Hello and welcome to another episode of How to Understand X. Today we're going to be talking about integrals. And yes, I've talked about this several times, and I in fact actually recorded a full hour of this video, only to realize that I did not have my microphone plugged in. So if I sound slightly passive aggressive for the next however many hours we are going to be talking, that's most likely why. So I am just going to do a bunch of practice. My goal is that it is 7 p.m. right now, and I want to do integrals until I physically cannot do any further integrals, right? So I am just searching up integral practice, and I'm just going to go into however many problems I can do. There is this website called Paul's Online Notes, and I'm just going to be solving every single integral that I see for a good amount of time. And yeah, we'll just get into it. We will do area under the curve, indefinite integrals, integration by parts, partial fraction decomposition, a lot, as much as we can. So, without any further ado, let's get into the first indefinite integral problem, and that is the integral of 6x to the power 5 minus 18x squared plus 7 dx. Now for this one, we need to know sum rule because these are three separate functions, or sum and difference rules because this is a minus, and we also need to know the integral of x to the power of n. So if the derivative, let me do dx, if the derivative of x to the power of n is equal to n times x to the n minus 1, already, not starting on the greatest of starts, but we have n times x to the n minus 1, we can just have n minus 1 and what's the opposite or the inverse operation of addition? That's going to be, inverse operation of subtraction is addition, so we need to have n plus 1 in the numerator, in the exponent. Oh my god. Yeah, this is not going to be a great video, but when we do the derivative, we have to do subtraction. So when we do the integral, or the inverse of differentiation, we need to do addition, or the inverse of subtraction, and you want this n plus 1 to cancel out with another n plus 1, so that this x to the power of n is by itself. It doesn't have a coefficient, so in order to cancel out, we have to have 1 over n plus 1 times x to the n plus 1, right? We need this n plus 1 and this n plus 1 to cancel out, so that we have, no coefficient for this x to the n, and then n plus 1 minus 1 is just going to be n. So that's how you get the integral of x to the power of n. It's 1 over n plus 1 times x to the n plus 1. And so let's do this one. We have constant rule as well. So c f of x, this integral with respect to x is equal to c times the integral of f of x with respect to x. So when you have this 6 out here, we can just put it on top of our n plus 1. So 5 is going to be n, 5 plus 1 times x to the 5 plus 1 minus 18 over 2 plus 1, because n is going to be equal to 2. 2 plus 1 times x to the 2 plus 1, and then plus 7 over 0, because x to the power of 0 is just 1. So the term that's attached to 7 is just going to be 1, or x to the power of 0. So we have 0 plus 1 times x to the 0 plus 1. And I'm actually just going to ask you to memorize that this integral of 1 with respect to x is x. I could continue to show the work for this, but I'm hoping that at a certain point it just kind of comes naturally. But we have 6 over 5 plus 1, so 6 over 6, which is just going to be 1, times x to the 5 plus 1, or x to the power of 6, minus 18 over 2 plus 1, so 18 over 3, which is 6, times x to the 2 plus 1, or 3, plus 7 over 1 times x to the 1, so 7x. And then we have plus c. Whenever we're doing an indefinite integral, there's no bounds to c if c has any value. So when we have a indefinite integral, we need to account for this constant of integration. When you do the derivative of a constant, you are going to get 0, right? Because if you have y equals, let's come up with some random 2. This is a horizontal line, and this is the y-axis. So on this horizontal line, if you pick any points on this line, the tangent line and the slope of that tangent line is going to have a 0 slope, right? It's going to be also horizontal. So derivative of a constant 0. So every time you do indefinite integration, you need to account for that potential constant. All right? And interesting. So, yep, we did get that one correct. Okay, that's funny. We have another problem, our second one. This is just going to, remind us of how to see operations. We have the integral of 6x to the power 5 dx minus 18x squared plus 7. And this 18x squared plus 7 is not part of this integral. Once you have dx, that's when you stop integrating because there's no further operations happening. Everything that's happening within the integral is happening before you see with respect to x because you are integrating with respect to x. So this negative 18x squared plus 7 is completely unaffected by this integral. And so we said that this was 6 over 5 plus 1 times x to the 5 plus 1. So this is going to be 6 over 6 times x to the 6 minus 18x squared plus 7. So we're going to have x to the power of 6 minus 18x squared plus 7 plus c. This c is still going to be attached to this integral instead of the total integral. So yeah, that was relatively intuitive. Let's do some further indefinite integrals. We have, again, this is, relatively similar to what we've been doing. We have the integral of 40x cubed one second. We have the integral of 40x cubed plus 12x squared minus 9x plus 14 dx. And all of this is preceding the dx, so this is just the sum and difference of many different functions, but we still have to solve this normally. We have 40 over 3 plus 1 times x to the 3 plus 1 plus 12 over 2 plus 1 times x to the 2 plus 1 minus 9 over 1 plus 1, again, x to the power of 1 is x, times x to the 1 plus 1 plus 14 over 0 plus 1 times x to the 0 plus 1. So this is going to be 40 over 4, or 10, x to the power of 4 plus 4x cubed, 12 over 3 times x to the 2 plus 1 minus 9 over 2 x squared plus 14x plus c. And the following problems are actually pretty much the exact same, except they shift the position of the dx to really reinforce that idea that when you are calculating integrals, you are only calculating up to the point you see dx. So, since we already did the antiderivative of every single term, we know how the antiderivative works, so I don't think it's really necessary to do those. And yeah, let's go into, oh, okay, we're getting a little bit more interesting. Well, in a little bit, but we do have some more stuff for us to actually do. We have the integral of 4x to the power of 6 minus 2x cubed plus 7x minus 4. This is a little bit dry, but we know we can do it. So we have 4 over 6 plus 1 times x to the 6 plus 1 minus 2 over 3 plus 1 times x to the 3 plus 1 plus 7 over 1 plus 1, not 2, 7 over 1 plus 1. Okay, can I click the pen? There it is. 7 over 1 plus 1 times x to the 1 plus 1. And then we have minus 4x. Again, we said that the integral of 1 with respect to x is going to be x. And that might actually be, it's not really a proof, but a visual representation if dx, almost forgot that. So all of this falls under dx. The reason that the integral of 1 with respect to x, you could just, use the definition of the antiderivative of x to the power of n, but I actually like to think back to instantaneous rate of change. If the rate of change is constant, then at this point, the slope of the tangent line is going to be the same as the slope of the tangent line here, right? And the only way that you can have the slope of a tangent line be equal to the slope of another tangent line is if those two points fall on the same curve. And since this slope is constant, that means that the line that connects those two is a line, which is, cool, at least to me. But yeah, that's just another representation of why the integral of 1 with respect to x is x. And then we have 4 over 7 times x to the power of 7 minus 2 over 4, so 1 over 2, x to the power of 4 plus 7 over 2, x squared minus 4x plus c. I'm hoping that by now you can start to see how, this power rule, 1 over n plus 1 times x to the n plus 1, isn't as scary as it might seem. And it's actually relatively intuitive. You're just trying to undo differentiation, so you have to use addition instead of subtraction, and then division instead of multiplication. So I feel like it makes some sense. Let's see if that's right. Okay. And then we have the integral of z to the power of 7 minus 48z to the power of 11 minus 5z to the power of 16 with respect to z. Alright, so we have n is equal to 7, so we have 1 over 7 plus 1 times z to the 7 plus 1 minus 48 over 11 plus 1 times z to the 11 plus 1, and then we have minus 5 over 16 plus 1 times z to the 16 plus 1. So let's do that. We have 1 over 8 z to the power of 8 minus 48 over 11 plus 1, so 48 over 12, which is 4 z to the power of 12 minus 5 over 17 z to the power of 17 plus c. And you can actually differentiate to really make sure that you got it correct. If you have this is n and this is 1 over n, then n times 1 over n is going to be 1. And then 8 minus 1 is 7, so this derivative is z to the power of 7. And, you can do that for all of these, but I don't really think it's necessary. So I'm just going to kind of go into the more crazy looking ones. Well, in a little bit. Let's finish these ones. I promise. We are going to have some more fun ones in a little bit. We have to get through some of this stuff before, though. We have the integral of 10t to the negative 3 plus 12t to the negative 9 plus 4t to the power of 3 dt. Now, you shouldn't be afraid of these negative exponents. The only negative exponent you should be afraid of is t to the negative 1. Because if you do 1 over negative 1 plus 1 times t to the, or x to the anything, negative 1 plus 1, you'll have 0 in the denominator. So 1 over 0 is not going to work out. We have to use our definition of the derivative of ln, which we can very quickly prove. And, just for fun, we might as well prove the derivative of e to the power of x, even though I think I've already done this one, because in order to do my definition, or my proof of the, it's not mine, isn't like I didn't come up with it or anything, but it's like the proof that I prefer of the derivative of ln x, we actually need to know the derivative of e to the power of x. So very quickly, let's go back to our definition of the derivative. That is the limit as h approaches 0 of f of x plus h minus f of x all over h. So let's do this one with e to the power of x, or f of x equals e to the power of x. So we're going to have, well, let's plug this in. We're going to have e to the power of x plus h minus e to the power of x all over h. And then using using our understanding of exponent properties, if they have the same base, then addition between the exponents is just multiplication. So we have e to the power of x times e to the power of h minus e to the power of x all over h, and then e to the x is common to both of those, so we can have e to the power of x times e to the power of h minus 1 all over h. And then from here, we can actually just set e to the power of x times e to the power of h minus 1 to some number n. So e to the power of x times e to the power of h minus 1. And so let's try to express h in terms of n so that we have both the numerator and the denominator in terms of h. So, well, we have to add, it's not e to the x times e to the power of h. It's just going to be n equals e to the power of h minus 1. So we add 1 to both sides. N plus 1 equals e to the power of h. And then we get ln of n plus 1 is going to be equal to h, right? Because we want that e to cancel out. So ln of n plus 1 is equal to h. So let's write that down. We have, well, actually, let's do something really quickly. We can bring this e to the power of x outside of this limit, right? This is the limit as h approaches 0 of all of this. And based on our limit properties, we know that any factor that is common to and all of the terms in a limit can just be pulled out. Kind of like how constants can be pulled out of derivatives and outside of integrals, but limits automatically kind of define derivatives and integrals. So it's just a limit property that extends to other things that limits kind of introduce. But yeah, we can just pull this e to the power of x out, and so we're going to have, after all of this, we're going to have e to the power of x times the limit as h approaches 0 of n over, this is supposed to be an h, over, and this is supposed to be an h. Maybe I should use a different term instead of h. All this over ln times n plus 1. And so if we do a 1 over n times this, and then, I don't know why I put 1 over 2 there. We want this numerator to come out to something nice. So we have, okay, apparently that doesn't want to undo itself, so we're going to have ln n plus 1, and if we multiply both the, okay, what is wrong with me? 1 over n times n, and then 1 over n times n, we can just cancel out these ln's, these n's, and then using our natural logarithm properties, we can just bring that n plus 1 to the power of 1 to the n, or 1 over n. So we're going to have 1 over ln of n plus 1 to the power of 1 over n. And this is just one of the definitions of e, right? So, well, kind of spoiling it, but we can actually use limits within the ln, right? Because ln is a continuous function. So when you bring the ln, so let's define e real quick. It's the limit as n approaches 0 of 1 of n plus 1 to the power of 1 over n. So yeah, that's just one of the definitions of e. And if we can, well, we already changed our bounds from h to n because we're using n now. And as n approaches 0, h will approach 0 because, I mean, it just kind of does because, like, let's go back to n equals e to the power of h minus 1. If you have n is equal to 0, then 1 is equal to, negative 1 is equal to something. When you bring that 0 to the other side, so you have positive 1, e to the h, you solve for h, you're going to have h equals 0. So as n approaches 0, h will be approaching 0. So you can do the limit as n approaches 0 of all this. I really am having trouble differentiating between h and n. I don't know why. I know they're both, letters with similar ways of writing, but wow. The limit as n approaches 0 of 1 over ln, n plus 1 to the power of 1n, all of this in parentheses, you can bring that limit as n approaches infinity inside of the ln because ln is a continuous function and limits can be applied to continuous functions. So that's another limit property. I guess it's also kind of a natural logarithm property, but you can just bring that limit as n approaches 0 inside, and you'll have 1 over ln of the limit as n approaches 0 of n plus 1 to the power of 1 over n, which we said was going to be e. So we're going to have 1 over ln e, so ln e is equal to 1, and then this is still multiplied by that e to the power of x. So yeah, went on quite a bit of a tangent, but that's why the derivative of e to the power of x is e to the power of x. And now that we know what the derivative of e to the power of x is, we can do the derivative of ln x. So let's write that down. We're going to start with y equals ln x. And then we can write this as e to the y is equal to x, right? We have these two functions, so we can do an operation, e to the power of that, on both sides, and we'll have e to the y is equal to x. And then using implicit differentiation, we can do the derivative of e to the power of y with respect to x. So that'll be dy of e to the power of y times dy dx is equal to d dx. We're doing d dx of both sides, by the way. D dx, and d dx should be in front of the x, but d dx of x, and this is d dx of x. So this is going to be e to the power of y times dy dx is equal to 1. And so when we solve for dy dx, because we're trying to find the derivative of y with respect to x so that we get the derivative of ln x, we're going to have dy dx is equal to 1 over e to the y. You might be thinking, oh no, we don't know what to do. But we said that e to the power of y is equal to x, so dy dx, or the derivative of ln x with respect to x, is going to be 1 over x. So y prime is equal to 1 over x. Very long tangent from what I was trying to say, which is that when you have a negative exponent, you shouldn't be afraid unless that negative exponent is negative 1. Because if you do 1 over negative 1 plus 1, you're going to get 1 over 0. And if you, well, by this point, I'm hoping that you just kind of know that the exponent, if it's negative 1, then it will be 1 over just a singular variable. But when you have 1 over a singular degree variable, you just do ln. But, yep, let's just kind of go back to what we were supposed to do. And that is this integral that we have in front of us. So this is going to be 10 over negative 3 plus 1 times t to the negative 3 plus 1, right, plus 12 over negative 9 plus 1 times t to the negative 9 plus 1, and then plus 4 over 3 plus 1 times t to the 3 plus 1. So this is going to be 10 over negative 4, so negative 5 over 2. And then this is t to the negative 2, so 1 over t squared, right? And then, wait, let me think about this. Does that make sense? Oh, well, whoops. Sorry. This is actually going to be negative 10 over negative 2, which is just negative 5, not negative 5 over 2, times t to the negative 2, plus 12 over negative 9 plus 1, so negative 4 over 3. Let's even write that as negative 4 over 3, because 12 over 8 is going to be, oh no, what? It's 3 over 2. Wow, that fraction threw me off. It's going to be 3 over 2 minus 3 over 2 times t to the negative 8, so t to the negative 8, and then plus 4 over 3 plus 1, so 4 over 4, times t to 3 plus 1, which is going to be t to the power of 4. Okay? And then this is going to be plus c. We can simplify this and say that this is 3 over 2t to the power of 8. And this is going to be, this is going to be negative 5 over t squared. Okay, great. And, yeah, I think that's, good practice. Now let's do another very similar problem. We're going to have, let's go into this. We have the integral of w to the power of negative 2 plus 10 times w to the negative 5 plus minus 8 with respect to w. So this will be parentheses. These are all separate functions, so we can kind of sum and subtract as necessary. And then we'll have 1 over negative 2 plus 1 times w to the negative 2 plus 1 plus 10 over negative 5 plus 1 times w to the negative 5 plus 1, and then minus 8w. We said that if it's the integral of 1 with respect to w or with respect to x, we're just going to have w and or x. So we're going to have negative 1 over 2 plus 1, so negative 1, times w to the negative 2 plus 1, so 1 over w. And this will be plus or minus 10 over negative 4, so negative 5 over 2, times w to the negative 4, so we can put that in the denominator. And then we have negative 8w plus c. Okay, perfect. And now we have another freebie. We have the integral of 12. Whoops. We have the integral of 12 with respect to y. So let's do that one real quick. Integral of 12 with respect to y. This is going to be 12y, as we've said, plus c. So we have 12y plus c. And now we actually get into some more interesting stuff. We have the cube root of w plus 10 times the fifth root of w cubed. Now, this is all with respect. Oh, I was about to say this is a lot more interesting than I thought, but this is just going to be a cube root of w. And then all of this is with respect to w. If this was actually y, then we wouldn't have to integrate with respect to y, so we wouldn't have to convert y into anything. We just need to add a w on the end. Cube root of y would be treated as a constant instead of as a fraction. We can even, not as a fraction, instead of as a variable, so we can even do that one real quick. The cube root of y, this integral with respect to w, will be the cube root of y times w. Y is not a function, at least in the way that we are writing it right now, so it'll be treated as a constant, and derivative, or the integral of 1 with respect to dw, with respect to w, is going to be w. Alright, so let's do this one. We have cube root of w, so w to the power of 1 over 3. If this is w to the power of 1, inside of a cube root, you put the exponent that's under the radical over the, root, strength, root, what's the correct term? The root's order, probably, but with w to the power of 1/3 plus 10 times w to the power of 3 over 5, and we don't need to worry about this one either. We have 1 over 3 plus 1 times w to the 1 over 3 plus 1 plus 10 over 3/5. Can't even read my own handwriting. 3/5 plus 1 times w to the 3/5 plus 1. Alright, so this is going to be 1 over 1/3 plus 1, so 1/3 over 4/3 times w 4/3 plus 10 over 8/5, so 3/5 plus 1 times w to the 8/5. And we can simplify this by simply flipping those fractions. And so this will be 3/4 times w to the 4/3 plus 10 times 5 is going to be 50 over 8, which we can write as, what are we going to write this as? It'll be 25 over 4 times w to the 8 over 5, and then plus c. And you could rewrite this in terms of radicals. You know, this could be like cube root of w to the power 4, and this will be the 5th root of, well, 25 over 4 times the 5th root of w to the power of 8. But honestly, that's kind of unnecessary. As long as we know what we're doing, this is the correct antiderivative. So even if we have fractional exponents, even if we have negative exponents, we just need to follow that power rule because, you know, it works. So yeah, there's a few more of these similar types, and we can keep doing them. Doesn't hurt. Yep, let's do 4. Let's erase this. I'm gonna start skipping these now because this is getting a little bit boring in my opinion. It's mostly power rule. I want to get into crazier stuff like sine and cosine and inverse trig and integration by parts, and you know, I want to get crazy, but we're staying relatively tame. We have 7 over 3y to the power of 6 plus 1 over y to the power of 10 minus 2 over 3, or the cube root of y to the power of 4. And this is all with respect to y. Okay, so this is 7/3 times y to the negative 6, right? If we rewrote that, this is plus y to the negative 10 if we rewrote that. And then this is y to the power of 4 over 3 and negative 4 over 3. So we have minus 2 times y to the negative 4 over 3. So let's do this one. Okay, we have, let's put the 7 over 3rd in the numerator, even though it'll make it a little bit difficult to look at. It's going to be consistent. We have 7 over 3 over n plus 1, so negative 6 plus 1, times y to the negative 6 plus 1 plus 1 over negative 10 plus 1 times y to the negative 10 plus 1 minus 2 over negative 4/3 plus 1 times y to the negative 4/3 plus 1. And this is intimidating looking, but it's okay. You know, we have negative 6 plus 1, so negative 5. 7/3 divided by negative 5 is going to be negative 15, right? So because when you bring that negative 5 into the numerator, it'll be 1 over negative 5, so we'll have negative 7 over 15 times y to the negative 5, and then we will have negative 1 over 9 times y to the negative 9, and then we'll have negative 2 over, negative 4/3 plus 1 is negative 1/3, so this will be 2 over 1/3, which is going to be 6. That 1/3 will become, just 3 when you bring it to the numerator, so we have 6 times y to the negative 1/3. And again, you can write this in exponent form if you'd like, but let's very quickly check our work. Yep, okay. That's great. Oh, I forgot to have a plus and then a plus c. Very important. And now we have, now we can get into some of the crazier stuff. We have, well, it's not going to get too crazy just right now, but it'll be at the very least more interesting. We have this trig one. We have the integral of sine x plus 10 cosecant squared x dx. And now, I am not a fan of memorization. I do not like teaching people to memorize. I do not like being told to memorize things. But the trig functions tend to be more memorization. We can do the derivatives. We actually proved the derivatives a little while ago. We know how the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Derivative of tan is secant squared. And we did the, not arc, but we did the, co-function derivatives as well. We got cotan was, well, don't want to spoil it, but we did cotan, we did cosecant, we did secant, but, it's going to be mostly memorization for those ones. So let's, go through them. We have the derivative of cotan. Let's say this is sine, this is cosine, this is tan. So let's do cosecant first, actually. We'll have cosecant is going to be negative cosecant x times cotan x. And secant will be sec x tan x. And then cotan will be cosecant squared, or negative cosecant squared. Okay. That was just not working out. Negative cosecant squared. And yeah, this is just kind of be memorization. I know it sucks, but it just is. You can actually solve these. We'll have, this is 1 over sine. So if you wanted to do the derivative, you would have 1 prime, so 0 minus 0 times the derivative of the, well, okay. We have f prime g minus fg prime over g squared if f is the numerator and g is the denominator. So f prime is going to be 0 times g, which is sine, so 0, minus the derivative of sine, so cosine. So we have negative cosine over sine squared, and that can be written in that way, I think. Let me think about that, actually. 1 over sine times, because you have a negative cosine over sine squared, so you can write it as negative 1 over sine times cosine over sine, which is going to be negative cosecant times cotan. Same with secant. Secant is 1 over cosine, so let's even write that out. 1 over cosine, so you do f prime g minus fg prime over g squared, so you have f prime, which is 0, times g, which is cosine, so you have 0 minus derivative of, 1 times the derivative of g, so that'll be negative sine, so you have 0 minus sine, which is going to be positive sine over cosine squared, and then that can be written as 1 over cosine times sine over cosine, which is secant times tan. And then cotan, that derivative is also similar to how you'd calculate the derivative of tan. Sine and cosine, those are like our primary derivatives, and you actually have to do proofs for those. But, cotan, that'll be just cosine over sine, which is another quotient rule. This one's a little bit more mathy. So for this one, you have to do derivative of f, so negative sine, times g, so negative sine times sine is negative sine squared, and then you have f times derivative of g, so you have cosine, you have negative sine squared, wait, is that correct? Yeah, negative sine squared minus cosine times sine derivative, so cosine squared, so you have negative sine squared minus cosine squared, you factor out the negative, and then you have negative out in the front, times sine squared plus cosine squared over sine squared, which is going to be 1, because sine squared plus cosine squared is equal to 1 over um, sine squared, which is cosecant squared, and you can't forget that negative out in the front. Um, I mean, I kind of did those, but like for us, it's probably best if we just kind of remember these. So yeah, we have negative cosecant squared sine x is what we have in our original one. So if the derivative of sine x is cosine x and the derivative of cosine x is negative sine x, then the antiderivative of sine x is going to be negative cosine x. So that when we differentiate this, we get this negative sine x. So yeah, it's going to be negative cosine x. And then plus 10 cosecant squared x. If we said that negative cosecant squared is the antiderivative of cosecant, then this will be negative 10. No, not cosecant. We said that negative cosecant squared was the antiderivative of cotan, so this will be negative 10 cotan x, because this is negative cosecant squared, and we want these to cancel out. Oh, that's not how it works. We want this negative to become, wait, what? Yeah, no, we want this negative to multiply to another negative so that we get that positive. And this is going to be plus c. Again, this is memorization, which I personally dislike, but, it works. So, yeah, at least for trig, I think it's important. And let's look at what else we have. Okay, we have a t squared minus 1 times 4 plus 3t. You might try to do some type of integration by parts. You might try to make this more complicated than it needs to be, but we can just write this sum, or this product of two functions, as the sum of a bunch of terms. So if we just distribute this t squared minus 1 to this 4 plus 3t, we'll have, let's actually mix that 3t and 4 so that we can do this a little bit quicker. Or, well, it won't be quicker, but we can see a little better. We have 3t cubed plus 4t squared minus 3t plus 4t. Then we just do this integral with respect to t. And so we have 3 over 3 plus 1 times t to the 3 plus 1 plus 4 over 2 plus 1 times t to the 2 plus 1 minus 3 over 2 t squared. I'm skipping steps. It's kind of like second nature at a certain point. I'm hoping that eventually come to you, but 3 over 1 plus 1 times t to the 1 plus 1. And then this will be minus 4, not 4t dt. It's just going to be minus 4. I don't know why I wrote all of that wrong, but negative 4 and then dt. So this will be negative 4t, as we said. And then this will be 3/4 t to the power 4 plus 4 over 3 t to the power 3 minus 3/2 t squared minus 4t plus c. And yep, that's correct. Let's do some more examples. That's interesting. Okay, let's do it. We have two rather interesting ones in succession. We have square root of z times z squared minus 1 over 4z, and this integral with respect to z. So let's do that one. So again, we could maybe do integration by parts, because this is the product of two functions, but it is just so much easier to distribute and then do power rule for every individual function. So we have z squared times z, so z squared times z 1/2, and then this is minus 1 over 4z, so 4 times z to the negative 1 times also z to the 1/2. And so, since we have the same base, we can add the exponents. We'll have z to the power of 5 over 2 minus 4z to the negative 1/2. All right, and let's see if that makes sense. Yeah, I think that's fine. Yeah, no, we're good. And then we do the integral with respect to the z of all of this. So we have 1 over 5/2 plus 1 times z to the 5/2 plus 1 minus 4 over negative 1/2 plus 1 times z to the negative 1/2 plus 1. So we're going to be left with negative 4 over 1/2, which is going to be negative 8 times t to the 1/2. And then 1 over 5/2 plus 1, that's going to be 1 over 7/2, so 2/7 times z to the 7 over 2 minus 8t 1/2, and then this is going to be plus c. And, we can simplify this to radical, but that's not really necessary, as long as we see how to do the antiderivative of this just by distributing. So I'm hoping that these examples kind of teach you one very important thing about using that power rule. If and when you have a product of two functions, it is just automatically so much easier to just distribute. Just distribute as quickly as you possibly can so that you have the sum of different terms and then just integrate those separately. But as I promised, we did have another interesting one immediately after. We have x to the power of 4, x to the power of 4 minus the cube root of x all over 6 to the power 6 times root x dx. Now we are not able to do the opposite of quotient rule in integration. We can undo product rule, but we cannot undo quotient rule. And even if we were to, how would it possibly look? We have 6 root x, and that's supposed to be the square of something, of some f prime g minus fg prime. It's not going to work out. So we're going to have to do what we did with the distribute, but we just need to split this fraction. So we have x to the power 4 minus the cube root of x. So we can write this as x to the power 4 over 6 root x minus the cube root of x, all over 6 root of x as well. Same denominator. And then this could be written as x to the power 4, 1 over 6 is brought out, 1 over 6 times x to the power 4 times x to the negative 1/2, and then this can be subtracted, negative 1 over 6 x to the power of 1/3 minus, or times x to the negative 1/2. Alright, and so let's simplify this just a little bit. When you have same bases, you simply add. So you're going to have 1/6 times x to the 4 minus 1/2. That's going to be 3 1/2, so 7/2. And then minus 1/6 times x to the 1/3 minus 1/2, so negative 1/6. So 1/6 times x to the negative 1/6. And then we'll just do the integral of this. So 1 over 6 in the numerator, 7/2 plus 1, and then x to the 7/2 plus 1 minus 1 over 6 times, or over negative 1/6 plus 1 times x to the negative 1/6 plus 1. Alright, great. From here, what do we want to do? We have to simplify this a little bit. We have 1 over 6 over 7/2 plus 1, so that's going to be 9 over 2. 1 over 6 times 2 over 9. This will cancel, this will cancel. We'll have 1 over 27. X to the 9/2. And then we will have negative 1/6 plus 1, so 5/6 minus So negative 1/6 over 5/6. So that will be 6, 5, 1/5. Is that 1/5? I think that's 1/5. Or wait, what? 1/6 times 5 over 6, 6 over 5. I think it's correct. Wait. Let me think about this. So we have negative 1 over 6 over negative 1 over 6 plus 1. So 5 over 6. 1/6 times 6 over 5 is 1 over 5. Oh, obviously. So never mind. We have negative x. Let's put this correctly. We have negative 1 over 5 x to the 5/6. I was getting tripped up because I thought that this 5 and 5 would cancel out, but then I just completely forgot this denominator of 6. So we do get the actual thing. And that one was pretty intricate. Let me actually check if I did get this one correct. If it would load. Wow, this is very slow. Might need to pause recording because this is very slow. Okay. Let me just try and reload. Okay. Well, this is taking a weirdly long amount of time, so I'm going to... We'll see if it loads at some point, but I can still see the previous page, so I'm just going to continue forward. I'll keep that in my memory bank. Let's hope it was at least relatively similar. I don't think I can remember, 1 over 27 or whatever it was, times x to the 9/2 minus or plus 1/5 times x to the 5/6 or something like that. I don't know. But let's just go straight into the next example. And this one's another slightly more interesting one. We have 2 cosine w minus secant w tan w. So we said that secant tan, or the product of secant and tan, that is going to be tangent, or secant, that derivative. So this is obviously integrated with respect to w. So this is going to be 2 sine w minus secant w. So that you just have to do the format of the original one, and then you just kind of translate it to the actual derivative. And wow, it still hasn't loaded for that previous problem, so I think I'm just going to not be able to do that. Let's see. This is definitely interesting. Okay. This one will test our understanding of the trig properties. So we have, right now we have 12, the integral of 12 plus cosecant of sine theta plus cosecant theta. Now, this is cosecant. It's not cosecant of that because that would be a lot more difficult to actually do. And then this is integrated with respect to theta. So cosecant is 1 over sine, and we have sine right here. So this will simply cancel out. We'll get cosecant theta times sine theta is just going to be theta. Is it theta or is it 1? Okay, wait. I think it might be 1, actually. Hold on. Yeah, no, that's just 1, actually. So we have 12 plus 1, and then cosecant and cosecant, that becomes cosecant squared. And we actually did another cosecant squared problem a little while ago, but this is just going to be what we said. This will be negative cosecant squared, which is the derivative of cotan, right? So you have 13 plus cosecant squared, and this is all integrated with respect to theta. So we have 13 theta minus cotan theta, right? This has to be derivative of the derivative of theta with respect to theta is going to be 1. So the antiderivative of 1 with respect to theta is going to be theta minus cotan theta, the derivative of which is going to be negative cosecant squared. All right? So let's just continue on our journey. Okay, we got some interesting stuff. Let's just keep following the line. Yeah, I'm never going to be able to see what the answer to that one was. I might, like, if I do get it eventually, I'll just kind of put it in the description what the answer is supposed to be. But, it's not working out. So let's do 4e to the power of z. This with plus 15 minus 1 over 6z dz. So this is going to be 4e to the power of z plus 15 minus 1 over 6 z to the negative 1. And then we said that e to the power of x, that derivative with respect to x, is going to be e to the power of x as well. So the integral of e to the power of x, or e to the power of z with respect to z, is going to be e to the power of z. So, and the constant in front does not affect it. Again, integral of c f of x with respect to x is going to be c times the integral of f of x with respect to x. So, yep, that 4 does not get affected by any integration, even though the integration doesn't actually affect anything itself. And then this will be plus 15z, integral of 1 with respect to z, minus 1 over 6 over 1 over 6th. Well, not that. It'll be n plus 1, so negative 1 plus 1. And we actually fell into a little trap, right? So this is going to be 1 over 6th times 1 over z, right? We can't divide by 0. So that, like, proof that I did a little while ago, we're just going to have to apply that again. Antiderivative of 1 over z, or 1 over x with respect to z or x respectively, is going to be 1 over 6 times ln z. Well, I mean, yeah, actually, no, we're good. I forgot that this is the integral with respect to z, and this is just the actual answer. But since we cannot do negative 1 plus 1 in the denominator, we just have to memorize that this is the antiderivative of 1 over z, even though I'm hoping that the derivative proof that I kind of showed was a good way of seeing it, because, I mean, if y equals ln x, and, e to the power of y equals x, and then dy dx of, times e to the y is equal to 1, and then dy dx is equal to 1 over x, because e to the y is equal to x. And then the integral with respect to x and the integral with respect to x should just go back to original y is equal to ln x, right? This was just undoing all the operations that got us to here. It's a cycle. So yeah, another way to think of that. But then the antiderivative of 1 over x is, or 1 over z in this case, is going to be ln. All right. So let's keep going. This is going to be plus c, obviously. And what else do we have? This is another rather interesting looking one. Even though it's actually not too difficult of a thing to do. We have t cubed minus e to the negative t minus 4 over e to the negative t. All of this integrated with respect to t. And so we have 1 over 3 plus 1 times t to the 3 plus 1 minus, we can split this fraction into two fractions, negative e to the negative t over e to the negative t, minus, so plus 4 over e to the negative t dt, and this will be, well, let's just say that this is that integral and we already solved this one. This will be 1/4 t to the power 4, and then this will be the integral of 1 plus 4 e to the power of t. E to the power of negative t, or 1 over e to the power of negative t, would just be regular e to the t, and then integral of 1 with respect to t is going to be t, integral of e to the power of t with respect to t is going to be e to the power of t, and then the constant doesn't affect anything. So we're going to have 1 over 4 t to the power of 4 minus t plus 4 times e to the power of t plus c. And yep, now we're going to get into some of the more interesting ones in my opinion. Well, I mean, these are fine, but I really do want to get into, some of the more difficult integrals out there and try and solve them. So we have the integral of 6 over w cubed minus 2 over w with respect to w. So what's that going to look like? Well, 6 over w cubed is going to be 6 times w to the negative 3. So we're going to have 6 over negative 3 plus 1 times w to the negative 3 plus 1. And then minus 2 over w is going to be minus 2 times 1 over w. So we're going to have negative 2 ln absolute value of w plus c. So 6 over negative 2 is going to be negative 3 times w negative 2 minus 2 ln w plus c. Again, I know I'm going a little bit fast for these ones, but I'm hoping that we're picking up on this kind of like pattern. Just make your expressions as simple as they possibly can be before you actually start integrating, because it will be a lot simpler than you think. You can't do product rule with integrals. You can't do quotient rule with integrals. The only rules that really carry over from integrals and derivatives is sum and difference rules. So whenever it is possible, make your function into the sum and difference of a bunch of functions. It might look more complicated than it originally was, but individually calculating each integral will be so much simpler than trying to calculate the integral of some enormous looking function. So let's get into these ones. This is going to require some knowledge of inverse trig. We have the integral of 1 over 1 plus x squared plus 12 over square root of 1 minus x squared with respect to x. Now, I think I actually, this is the integral of arctan, but I think I might have actually done a proof of this relatively recently. I'm still going to do it anyways because I really like this proof, but you can skip forward if you'd like. If you have y equals arctan x, then if you did tan of both sides, you'll simply cancel out. Tan of arctan is going to be just x. So you have tan y equals x, and then when you do the derivative of both sides, you'll have d dx of both sides, so d dx. So you'll have dy dx times secant squared y is equal to 1. So dy dx is going to equal 1 over secant squared y. So it's just going to be cosine squared y. And, you might stop there and be like, hey, we did this, but it's not going to work out as well as we want it to. So let's, write this in a slightly more substantial way. So from tan y, well, this could be, cosine squared arctan x is how you differentiate arctan, but this can be simplified much further. So let's just draw a right triangle where you have y is the angle, opposite over adjacent is tan. So if we have tan y is equal to just x, then opposite should be x, adjacent should be 1, and then we'll have, using Pythagorean theorem, we have a squared plus b squared, so 1 squared plus x squared is equal to c squared, which means that c is equal to the square root of 1 plus x squared. And then we do cosine. We have to do cosine squared of this. So if cosine is adjacent over hypotenuse, let's write 1 plus x squared, the square root of that. Cosine squared is going to be 1 over root of 1 plus x squared squared. So we're going to have 1 plus x squared. 1 plus x squared in the denominator under 1. And that's just, very quick proof of why arctan's derivative is going to be 1 over 1 plus x squared. And yeah, you can have the same kind of proof for square root of 1 minus x squared. And we can actually do a similar proof for this derivative. 1 over square root of 1 minus x squared is going to be the derivative of arcsine. So if y equals arcsine, then sine of arcsine of x, then sine y has to equal x. And then when you do the derivative with respect to x of both sides, you're going to have d dy of sine y, so cosine y times dy dx. Again, we're doing derivative with respect to x of a function that has y as its input, so we need to do implicit differentiation, d dx, and then this is going to be 1, so dy dx is going to equal 1 over cosine y. And then if sine y is equal to x, right, sine y is equal to x, we can redraw that right triangle. We have y is over here, x is opposite over hypotenuse, so 1, and then that means that 1 squared equals x squared plus a squared, and so a is going to be equal to the square root of 1 minus x squared, right? So square root of 1 minus x squared, and then cosine y is going to be, let's draw 1 over cosine, or try to describe 1 over cosine. If cosine is equal to adjacent over hypotenuse, then 1 over cosine, or secant, will be hypotenuse over adjacent. So that will be 1 over square root of 1 minus x squared, which is, again, going to be the derivative of arcsine. So from here, all of that was just to kind of go through why the integrals of these inverse trig functions are what they are. We have arctan x plus 12 times arcsine x plus c. Alright, let's go on to the next one. Okay, another relatively similar one. We have 6 cosine z plus 4 over square root of 1 minus z squared dz. So we're going to have 6 sine z, again, antiderivative of cosine is sine because the derivative of sine is cosine, so no negative necessary. And then we said that the square root, or 1 over square root of 1 minus x squared is going to be arcsine, so if we're using z instead, we're going to have 4 arcsine z plus c. Okay, that was relatively easy. We have a rather interesting one in a little bit. So, we have to find f of x if we are given f prime x and a specific point. So we have f prime x is equal to 12x squared minus 4x, and then f minus 3 equals 17. Okay, not 12, 17. So here we have the integral with f of x with respect to x. This is going to be the integral of 12x squared minus 4x with respect to x as well. So we have 12 over 2 plus 1 times x to the 2 plus 1 minus 4 over 1 plus 1 times x to the 1 plus 1. So this will be 12 over 3, 4 times x cubed minus 2 times x squared. And then this would be plus c, and this is f of x, right? Because f of x will be the antiderivative of f prime x, but then we have to solve for c. So if f of x is equal to 17 when x equals negative 3, then we have negative 3 cubed, which is going to be negative 27 times 4. Ah, man, I'm getting tired already. I can't really do this in my head. Well, it'll be 108, but, you know, this will be inefficient. We are going to do some definite intervals in just a little bit, so I think I might cheat and bring out the calculator, but I'll be doing the antiderivative part by myself, which is obviously going to be a lot more important. So, yeah, I'm sorry that I have to use a calculator, but it's not super late. It's like 8:30, but I am going to be doing this for quite a bit, and I'm already getting just a touch tired. Negative 3 cubed, negative 27 times 4 is negative 108, minus 2 times negative 3 squared, so negative 2 times 9, which is going to be negative 18. Let's write that down. Negative 18 plus c. So c is going to be 17 plus 108 plus 18. So we're going to have 143. So we're going to have 4x cubed minus 2x squared plus 143. And if we do the derivative of that, we're going to get 12x squared, and the derivative of that, we're going to get 4x. I'm actually not sure if this works, so let me plug this in. Minus 2 times negative 3 squared plus plus 143. Okay, and we did get 17 at the end of that, so we are doing something correct. And yeah, that's how we're going to be solving this. This is kind of like a very basic like introduction to the concept of differential equations, but we will get to that in a little bit. Now we have g prime z. G prime z is equal to 3z cubed plus 7 over 2 root z minus e to the power of z, and g of 1 is equal to 15 minus e. Okay, let's write this as a slightly more simple power function. So we're going to have to do the antiderivative with respect to z. So we're going to have to do 3 over 3 plus 1 times z to the 3 plus 1 plus 7 over 2 times z to the negative 1/2. Okay, yeah, I already evaluated this interval, so this is separate. Minus, well, we could do this one in our sleep, but now we have negative e to the power of z. And though for this one, we're going to have 7 over 2 over negative 1/2 plus 1 times z to the negative 1/2 plus 1. So this will be 1/2, so 7/2 divided by 1/2 is just going to be 7 times 7 times 1/2, or 7 times z to the 1/2 minus e to the power of z, and then this like integral on the left, this integral on the left will be 3/4, I can write 3/4 z to the 4th, and then plus all of this, and then yep, this will be our g of z, but this is plus c, so we need to plug in our 15 minus e, so we get 15 minus e is equal to 3/4, anything to, well, 1 to any power is just going to be 1, so 3/4 plus 7 minus e to the power of 1 is e. And so we're going to have 3/4 plus 7. What's that going to be? 31 over 4. 31 over 4. Wait, what? That doesn't make sense. Oh, plus c. I was like, 15 does not equal 31 over 4. But, yep, we have to have 31 over 4 plus c equals 15 because the minus e's actually just cancel out. And so that'll just be, like 29 over 4, I think. I'm pretty sure it's 29 over 4. Let's check. 3 over 4 times 1 to the power of 4 plus 7 1 to the power of 1/2 minus e. Well, I'll just keep the e by itself. Plus 29 over 4. Okay, yep, that's 15. And I just did not put the z equals 1. But when you plug in z equals 1, you'll just get 15 minus e. And when you do the derivative of all this, 3 over 4 times e to the power of 4, 4 minus, well, you put the n equals 4 in the front. 3 over 4 times 4 is 3. 4 minus 1 is 3. So you have 3 times z cubed. And then 1/2, you pull that out, you have 7 over 2. Z times 1/2 minus 1/2. 1/2 minus 1 is going to be negative 1/2, which is what we said. And then e to the power of z, that derivative is also e to the power of z. So, yep, that's correct. And this is going to be the last of these somewhat kind of boring problems. We do have quite a bit more interesting problems coming up soon. At least I hope so. I'm going to try and find some more difficult ones. So we have h, this is a double prime, so h prime t. We have h double prime of t minus 48 of t. Okay. Interesting. I think we might have to do a system of equations, but let me just write this problem correctly. This might actually be a interesting problem in and of itself. Equals 24t squared minus 48t plus 2. So h prime t, we can calculate this by now. We have 24 over 2 plus 1 times t to the 2 plus 1 minus 48 over 1 plus 1 times t to the 1 plus 1, and then 2 over 0 plus 1 times t to the 0 plus 1. So this is just going to be, what's this going to be? Well, this is going to be 8t cubed minus 24t squared plus 2t plus c. And then we have h of t is going to be 8 over 3 plus 1 times t to the 3 plus 1 minus 24 over 2 plus 1 times t to the 2 plus 1 plus 2 over 1 plus 1 times 2 over 1 plus 1 times t to the 1 plus 1 plus ct. Again, integral of 1 with respect to t is going to be t. So 8 over 4 is going to be 2. I'm running a little bit out of space. We have 2 times t to the power of 4. This will be negative 24 over 3, 8 t squared, or 8t cubed. And then 2 over 1 plus 1 will be 1. So we'll have t squared. And then this is plus ct, and then plus c1. Let's say that this is c1. Okay. So yeah, this is going to be, I think, a systems of equations, because we have the 2 points that they give us. h1 is equal to negative 9. Yeah, this is definitely systems of equations. H minus 2 is equal to negative 4. And we'll have to do systems of equations for a future couple of example problems. And so let's plug in -9. We're going to have -9. I'm just going to say these because, 1 to the power of anything is going to be 1. So this is equal to 2 minus 8 plus 1 plus c plus c1. So -6 plus 1, -5, -9 plus 5 is going to be -4. Let's just make sure, -2, -9 minus 2 plus 8 minus 1 is going to be -4. Yep. So we have c plus c1 is equal to -4. And then when you plug in -2, you're going to have 16 times 2, 32. Oh, let's just say this is -4 is equal to 32 minus 8 times -2 to the power of 3. So 8, 64, I believe. Yeah, positive 64. And then t squared is -2 squared, so plus 4 plus, minus 2c plus c1. And let me just make sure, that was correct. 2 times -2 to the power of 4 minus 8 times -2 to the power of 3 plus t, or -2 to the power of 2. And, yep, that'll be 100. 32 plus 64 is 96 plus 4 is 100, so, yep, that's correct. And then minus 4 minus 100. We're going to have -104. So -104, let me, here it is. -104 is going to be equal to -2c plus c1. And so we can actually subtract these two. We have c minus c, or c minus 2c, because we want these c1s to cancel, right? c1 minus c1 is 0. So if you do c minus 2c is going to be 3c is equal to -4 minus -104. So it's going to be it's going to be 100, right? Ooh, that's definitely not good. I mean, it's fine because we don't have to do anything too egregious, but yeah, that might be a little bit annoying to calculate. And then 100, let's see. So we have c equals 100 over 3, right? And then from here, we just have to do -4 minus 100 over 3, so that'll be like -12 minus, so is it just -112? Let's see, 100 over 3 minus 112 over 3, yeah, okay. So C1 is equal to -112 over 3, though that doesn't seem correct. Let's just look back at our original h of t. We have 2t to the power 4, so when you do that derivative, you get 8t cubed, and then 24t squared, which is what we originally had, and then 8t cubed. You do that derivative, you get 24t squared, and 48t, which is what we had. Then t squared goes to 2t goes to 2, which is what we had. So I think that antiderivative is fine. Plus ct goes to c goes to 0, which is fine. C1 goes to 0 immediately. So I think that's okay. Now let's actually plug in some values. We have 2 times 1 to the power of 4 minus 8 times 1 to the power of 3 plus 1 squared. I would just look at the answer key, but I'm not sure if it's my internet or this website, but it is just impossible. It's just impossible. It's not going to work out. Minus 112 over 3 Yep, and we did get -9, so that's fine. Now we just need to replug this in with -2, -2, -2, -2, and 100/3 times -2, and I don't think it'll mess that up too badly. And then that'll be -112/3. Huh. And we just did get -4, so yeah, it's a little bit ugly, but we did get the correct answer, which is obviously very good. And now we can actually get to some of the fun stuff. Or, well, we could do some definite integral practice, but honestly, I don't think we need that. We are pretty good at our normal integrals now, so let's get into some of the crazier stuff that integrals has to offer. Actually, you know what? I know it's kind of boring, but we should probably get into some definite integrals before we can get into integration by parts, partial fraction decomposition, improminent integrals, and multiple integrals. So let's look at some definite integrals really quickly. I'm just going to do like 3 or 4 examples of definite integrals, because if you can do the antiderivative and if you can do it consistently, then at a certain point the definite integral is just the antiderivative with values plugged in. It's not much more complex than that. So I think if you can handle normal antiderivatives, then this just seems fine, right? But that's just me. That's just my personal opinion. But let's get into some of these. Okay, so I just searched up definite integral practice. We're just going to do the first couple ones, and automatically we've started on a relatively unique first one. Let's see. One second. Okay, here we go. We have this rather unique integral, that being the integral from 0 to 1 of 5 over the square root of 9 minus 4x squared with respect to x. I kind of see well, let's look back at our arc sign notation. We have 1 over square root of 1 minus x squared. This is the antiderivative of this with respect to x is just arc sine x, and we have a similar looking thing right here, right? So for this one, I'm going to try and get some. I'm going to try and simplify this, right? So we're going to do some u sub, but we want this u sub to be a slightly unique u sub. You want this u sub to be just, how do I explain this? So, okay, so we have several functions. We have 9 minus 4x squared, we have square root of x, and then we have 5 over a function. We have 3 things happening. And I think that the most important one to look at is the 4x squared, because we want it to be either we want the 9 and the 4x squared to be, x squared, or we want this 9, or this 4x squared, to be equal to 9x squared, right? We want this to kind of be what we're going for, because then if we had 9 minus 9x squared and the radical, we could just take out a 3, because 3 is multiplied to all of this. This is like 1 minus x squared times 3. The root of all of that is just root of 9 is 3 root minus 1 minus x squared, and then we'd be able to do something. Right, so I'm going to try and make this, well, I'll stop, the nonsense, and we'll just say that u is equal to 2x over 3. right? And then when you differentiate u, because we have multiple functions right now, but 2x over 3 is probably the best thing to substitute for, so that we get a 9u squared. Because, let me say what I'm trying to say correctly. If we are trying to get the form of, say, 4x squared is equal to 9u squared, and then we just solve for u, u squared is equal to 4 over 9x squared, then u will become 2x over 3. I'm just trying to get the coefficients of 1 and x squared to be the same, so that I can format the denominator into that square root of 1 minus x squared, so that it looks like arc sine. And then from here, we have, well, let's say we go back to our u equals 2 thirds x. Then you differentiate with respect to x of u, so you'll get 2 thirds. Then you multiply dx to both sides, and then you get du is equal to 2 thirds dx, or dx is equal to 3 halves du. And so let's plug in du for here, and for like dx, 3 halves du for dx. And let's also plug in 9u squared for 4 x squared, which was the whole point of that. So you have 9x squared in there, and this is equal to 3 root 1 minus x squared, because we can factor out the square root of 9. So we'll have 5 over 3 root 1 minus x squared times 3 over 2, and then the 3's cancel, du, integral from 0 to 1, and we should just get 5 halves, and then arc, 5 halves 1 over square root of 1 minus u squared du, that integral from 0 to 1, which is going to just be arc sine of u, which we said that u was 2 thirds x, so we're going to have 5 over 2 times arc sine 2 thirds x, and then integral from 1 to 0, so I'm going to have to actually plug this in real quick. Arc sine 2 thirds minus arc sine 0 times 5. Okay, let's see. And divide by 2. Yep, okay, we did get 1.82, which is one of the answers, and we can continue going. And this one's another relatively interesting one. But yeah, that method of trying to format the denominator into one of the inverse trig derivatives that we know, that's a kind of weird looking like way of formatting, I know, but it's definitely important to remember that when you see like a square root of something minus another something, there can be like a way to format that denominator so that you can factor out something to get the like inverse trig functions that you are familiar with. So we have the integral from 1 to 3 of 5 over x squared plus 1 over x to the power of 5 minus cube root of x. Now this one's a little bit, blasé. We have 5x to the negative 2 plus x to the negative 5 minus x to the 1/3. Just reformatting these all in terms of power rule. And then we have 5 over negative 2 plus 1, x to the negative 2 plus 1, plus 1 over negative 5 plus 1 times x to the negative 5 plus 1 minus 1 over 1/3 plus 1 times x to the 1/3 plus 1. And this is, of course, with the bounds, so 1 to 3. So we're going to have negative 5 x to the negative 1 plus, minus 1/4 x to the negative 4th. and then minus 3/4 x to the 4/3. Well, I was about to say plus c, but this is a definite integral, so plus c is not necessary. We are given the actual like curve itself, so this will be the area under the curve from 1 to 3, and let's really quickly plug that in. 5 times 8 to the -1 minus 1/4 8 to the -4 minus 3 4. No, I'm very interesting commentary. So we get that, and then this will be minus -5 over 2. Ah, no, good. I thought I messed something up. 5 times 1 to the -1 minus 1/4 negative 1 to the -1. And then lastly, minus 3 over 4 times 1 to the 4/3. Let's see if we got the correct answer. Yep, 1.085. Perfect. So yeah, that was just another application of the power rule that we've been getting pretty familiar with now. So let's continue next. Okay, we finished those kinds of problems. This is interesting. We have a definite integral. So this is gonna be something. We have 1 over 4 plus 5 cosine x. The integral from 0 to pi over 2 dx is going to be equal to one of these things. So this is u sub. We have a function inside of a function, right? We have this in the denominator, which is obviously a function, and then we have the larger function of 1 over something. So let's let u equal 4 plus 5 cosine x. So, wait, what? No, that's not going to be working. Let's see. Oh, wait. Yeah, no, we are actually going to skip this one. This is going to require some knowledge of half angle formulas, which, I mean, we could, do, but, like, it's unnecessary to try and learn something completely irrelevant to the topic at hand, like, right now, of all times. So, let's just go completely in the opposite direction. Let's see. And actually, we're just batting 0 for 2 because this one requires understanding of polar form. So, yeah, that's not going to work either. Let's see. Khan Academy, you know what you're doing. Reverse power rule. Okay. This is a lot easier than what we've been doing. Doesn't hurt, though. Let's see. Let's go into practice. Let's say that we have the indefinite interval. Chill, Sal. Let's do this practice. Okay. Yep. So it just gave us the answer, but well, I just kind of did the answer because it was a little bit simple, but it was the integral from 2 to 3 of 6x squared cosine 2x cubed plus 1 in parentheses. Now, what is the function? A function that we can see automatically. U is inside a cosine, so we can say that u is equal to 2x cubed plus 1. We differentiate with respect to x. U is a function of x, but we need to do du dx, and that's equal to 6x squared. And so when we solve for dx, we just flip these two, and we will get dx is equal to du over 6x squared. So we can put that inside there. We'll get dx, so du over 6x squared. these two will cancel out, and this is cosine u. And then, so when we actually integrate this, we're going to have sine u. If the derivative of sine is cosine, then the antiderivative of cosine is going to be sine. So we're going to be left with sine u, which we said was 2x cubed plus 1. And so when we plug in 3 and 2 into this, we will get sine 55? Sine 55 minus sine 8, 16, 17, I think. Sine 17. I wish I could make like lines actually be drawn on command. I keep drawing lines on accident, which would be helpful for, you know, trying to draw axes or vectors, but I keep drawing lines when I don't want to draw lines, so that's kind of annoying. But, okay. Ooh, this is interesting. I mean, it's the same kind of problem, but there's more stuff happening, so they don't give us bounds. We're still working with just u sub, and these questions aren't even asking you to solve the u sub, just do the u sub, which is kind of not great, but you know, we can do it. We have, let's say, let's work with pi over 2 and 0, 0 to pi over 2. And then we have sine negative 5x to the power 4 minus, I don't know why I wrote it like that, minus x minus 6 times negative 20x cubed minus 1. What is our function inside of a function? We have this, which is going to be u. It's a function inside of the larger sine function. So when we differentiate u, we have u equals 5x to the power 4 minus x minus 6, or negative, and then we du dx, differentiate u with respect to x, we get negative 20x cubed minus 1. I'm just going to kind of skip the steps for these because, you know, at a certain point, it's going to kind of start coming to you. Now we have n times x to the n minus 1, so we bring that n out, times 4 minus 1, so 3, and then derivative of x is going to be 1, as we've said, and so when we multiply dx to both sides, and well, when we solve for dx, we should just get dx is equal to du over negative 20x cubed negative 1. So if this was dx, then we simply cancel out that negative 20x cubed minus 1 for both the numerator and the denominator, and we're just going to have du up here, and then negative, well, sine u here, and then if the derivative of cosine is negative sine, then the antiderivative of positive sine is going to be negative cosine. So negative cosine, and then 5, or negative 5x to the power 4 minus x minus 6. So this is going to be quite the interesting plugging. Well, you know, we could do it. So when you plug in 0, this is going to be pi over 2 to 0. I don't know, I did 2 to pi. But when you plug in 0, you're just going to get cosine of negative 6. What are the rules of negative cosine? If I remember correctly, cosine negative x is still cosine x, because, oh yeah, because it's an even function. It's symmetric across the y-axis, so regardless of whether x is negative or not, well, I mean, x is negative or not does actually impact the output a little bit, but, you know, it's symmetric across the y-axis, so it's an even function, so cosine negative x is the same as cosine x, and so you have cosine 6, and so you have minus minus, so we evaluated the second half of the integral, and now for the actual part of the integral, I'm just going to plug this in my calculator. I mean, I might be able to do some of this, but, you know, why would I do that? Negative cosine, negative 5 times pi over 2 to the power of 4 minus pi minus 6. and we just get something interesting. We get like 0.307 or something. So yeah, I just gave some random bounds, but that's how you would calculate it. No, you have the antiderivative, and then you plug in big F of b minus big F of a, or the antiderivative of the outer bound minus the antiderivative of the inner bound. And yeah, that's a perfectly fine way of representing this. I actually want to do one area and volume problem, so let's just search up volume integral before we can get into before we actually get into some of the integration by parts and other things that we were talking about. Volume integral examples. Sure. Let's just pick. Oh man, this is multiple integrals. Maybe I should specify exactly what I'm talking about. I'll just say solids of revolution. So I didn't actually do any practice problems on revolutions of a solid, which is, a big gap in that. But I mean, in my defense, I hate these kinds of problems. I just genuinely really dislike them with a burning passion. But it is supposed to be my job to be, fair and unbiased towards all math and their respective beauty or whatever. So let's just kind of do it. First practice problem that I see, it is the volume of the solid, volume of solid created when you rotate y equals root x, or the area between y equals 3 and y equals root x about the y-axis. Interesting. Maybe I should do x-axis first, but it's okay. We can handle it. Or can we? I think we could do it, but it's definitely gonna be a lot more annoying. Let's see. Now let me find a. I think we could do this. But it's just gonna be a bit of a jump. Maybe I might need to do 2 of these, or like 3 or whatever. But let's draw what's happening. So we have, this is the xy plane, right? And let's say that this is y equals root x, and then this is y equals 3, right? So the area of this, eventually, not eventually, at square root of 9, you will get 3. So let me redraw this y equals 3 a little bit closer to y equals root x. We'll have it somewhere around there. Yeah, that seems fine. This is going to be y equals 3, and this is the y-axis, the axis that we're supposed to revolve this area. So it's just asking for where these two intersect, right? So if we have this, the area, this point right there, we'll call that 9, 3. This is the intersection point between the y equals root x and the y equals 3, right? So if we were to try and find the area with respect to x, we would just do the integral from 0 to 9, the x values, of 3 minus root x, right? If 3 is like the limiting function of y equals root x, then 3 minus root x is just a good representation of what's happening. You have to do the function on top minus the function on the bottom, and then what's left is what's in between. And then you just do the definite integral, or you create a bunch of impossibly thin rectangles and just sum up the area of those rectangles. So that's how you'd find the area under the curve. With this, you just integrate with respect to x, but we have to find the volume of a solid revolved around the y-axis. So let's kind of try and draw what this might look like. So we have a revolution, so the base of whatever solid that we create has to be some kind of a circle, and then it'll just go out and down like this, right? If this is y equals root x, let me draw this slightly better. When, say, because this is supposed to be the the y-axis, right? If you have this point going like that, well, this is actually y equals 3. This like line across this base, y equals 3. And when you just have this revolution, you'll get this kind of cup-looking thing. And we have to find the volume of this, right? So how would we do that? In the way that we create very impossibly thin rectangles, another way to try and think of volume is a bunch of impossibly thin cylinders, right? Because let's like try and draw this as a side view. If this is how it is, right? This is like maybe an isometric view. If you were to look at this from the top and kind of off, you would see this kind of like a disc, like the whole base. But if you look at it directly from the side, you'll just see this flat shape. And if you split this flat shape into a bunch of very, very thin rectangles, very incredibly thin not very thin rectangles. If you make this into very thin cylinders, then you can just add up all of the cylinder volumes to get the volume of the entire solid. In the same way that we have to add up the areas of a bunch of rectangles to find the definite integral, or area under the curve, we have to add up a bunch of very thin rectangles. I keep thinking rectangles. No, this is cylinders. This is called the washer method or the disc method. And, well, washer is actually a different thing. This is called the disc method. But it's just when you come up with these very, very thin cylinders, and then you just add the volume of all of these cylinders up together to get the actual volume of the curve, right? So we are going to be integrating with respect to y. We are revolving around the y-axis instead of around the x-axis. So when we do a revolution like that, we actually have to change our x into y so that we can integrate with respect to y. So if y equals root x, then x equals root, or not x equals root y, because y equals root x is still the same. We can't actually change the graph itself, but we can have that if you square both sides, you'll get x equals y squared. That's a way of representing y equals square root of x in two terms of y. And so let's try and demonstrate what we're doing. If x equals square root of, or x equals y squared, then the how should I kind of try and define this? So the radius of any disk that you create, like let's go back to this real quickly. Like let's try and draw that thing. That's definitely not the center of the circle, but the radius of that circle is well, we said it's gonna be this intersection point, right? And that's x equals y squared. We said that this is x equals y squared. So the radius of the like circle, or the radius of this disk, or very thin cylinder, however you want to think of it, the radius of this disk is going to be y squared if you write this as a function of y. So if you have the area in terms of y, if this is the radius, then you have to do pi r squared, or pi y squared squared. So we're going to have pi times y to the power of 4. And then from here, you have to integrate from two y values, 0 to 3, not from 0 to 9. We are looking in terms of the y-axis. For each cylinder, the you're going from 0 to 3. So each radius, each x equals y squared, you'll be doing the definite integral from 0 to 3, not from 0 to 9. Because again, we are revolving around the y-axis. So this is going to be the integral from 0 to 3 of pi times x to the power 4 dy, or not x to the power 4. Sorry, we were just talking for like 5 minutes about how this is, we are changing our variable from x to y since we're revolving around the y-axis, and this is the integral of y to the power 4 with respect to y. And, you do 4 plus 1, so 1 over 4 plus 1, 5, and then y to the 4 plus 1, so 5, and then you have, you can bring that pi out, it is a number, and then you'll be integrating from 0 to 3, so 3 to the power 5 is like 243, I think. Yep, 243 over 5, and 0 times anything is 0, so you have 243 over 5 times pi. That is the volume of this solid. And let's do another actual practice one, because it's definitely important to understand what's happening. So let's try. Let me find a washer type problem. Yeah, okay, I found one. Let's see. Okay, so we have okay, this one's actually not too bad, so that's a good example to work with. We have the volume of a solid. This is the disk. This is the washer method. That was the disk method. But washer method is what it sounds like. A washer is like something used in a bunch of stuff. It looks like that. You have a hole in the center, which is what we want. So let's do what a washer would look like. So we have the volume of a solid. Volume of solid created when you rotate, when you rotate the region between y equals 2x plus 1, x equals 4, and y equals 3. Interesting. About the line x equals -4. So there's a lot happening in this already. But, let's just draw first. I think it's definitely helpful for when you are working with these kinds of problems. If you can't draw, at the very least try to visualize what's happening. But, I can't draw, and I still try to draw. But we have y equals 2x plus 1, so let's say 1, 3 would be somewhere around there. So that point, and then it'll go like that. And then we are going to be just x equals 4 is where this graph will stop, and then y equals 3. So I'm stopping directly at that first time that we have a y value of 3, so 1, 3, and then I'm also stopping at the first time that we have an x value of 4, so that'll be 4, 9. That's 4, 3. We could still, say what it is, 4, 3, and this will be 4, 9. And then you're trying to find the volume of this solid revolved around x equals -4. So let's draw that line, and let's try and think about how this would actually look. So, there's obviously going to be an enormous gap of nothing. There's just air in between, so we're going to have a kind of like an open cup, like a poorly made cup. That's what we're supposed to have, right? So let's kind of try and draw this. Not turning out well. Let's see. One more time. We're going to have like the circles, like the way it travels as you rotate it, and then a smaller circle representing where it kind of goes, or where it doesn't actually go. And then it'll be straight lines connecting those two, and then, another circle following the top circle. That's that's the best that I can kind of describe it. Just if you think about it in your head, if you have a rectangle and then you just rotate it around, you will be tracing a circle in the air, right? But if the, like, maybe just kind of think of a triangle and just rotate this triangle around your finger. When you rotate it around your finger, if the triangle is not explicitly touching your finger and you rotate it around, at the very center, you're going to create a circle of nothing. It'll just be a circle of air, but the arc, well, arc is going to be evoking some ideas of actual arcs. The circle that you are creating in the air at the very vertex at 4, 9, the the circle that you are creating will just be an empty circle, and the 4, 3, when you rotate that around, you are going to get the it'll follow the same circle as 4, 9, but it'll actually have a volume attached to it because 1, 3 and 4, 3 are connected. And when you rotate that, let me try and draw this slightly better. Again, we're gonna just kind of think of this as you have a circle of here, and then a circle of the same size, and then just there's like a mini circle. That's probably the best way to think of it. A mini circle where nothing's happening, and there's like a triangle connecting the two. So it's exactly the same as I wrote directly to the right of it, but if you can understand, or at least kind of sort of see what this would look like in your head, that's more than enough. And from here, we have to think, what would we be, how would we come up with a disk method for this? So, what I'm saying is that at the base of these, at the base of this, like, weird looking solid, I'll try and draw a much more head-on way of looking at this. At the base of this solid, there's this circle right there, and you are trying to find the area of a bunch of cylinders, right? But there's a bunch of empty space here. So if we were to draw a cylinder, let's even write it out here, and you just have empty space, how would you calculate the area of this, right? How would you calculate the volume of this even? So the way to do this is to just calculate the area of the larger circle and then subtract the area of the inner circle. This is also seen, well, we're just going to write this out really quickly. We're trying to find the area in terms of x. So area of a circle is going to be pi r squared, right? So the outer radius right now is, well, how do we write this? So we're going to be rotating this about some, so we're going to be rotating this about x equals -4. This x equals -4 is parallel to the y-axis, so we're going to have to integrate with respect to y. So let's rewrite this y equals 2x plus 1 in terms of y. I thought I was going to have one that revolved around the x-axis. I'll find another example, but let's write this y equals 2x plus 1 in terms of y. We would have y minus 1 over 2, right? If we solve for x. So 1/2 y minus, 1/2. And that's going to be the line, this line, that follows it, right? So the inner radius is going to be 4 plus that line, right? Because this is a distance of 4. So, yeah, it's a distance from 4, or actually, not from 4. So we have x equals 4 is this line right there, that value. And this, when you rotate it about this x equals -4, you will get the outer radius. You'll get the outer circle of that circle that we're trying to calculate, right? If we get the area of the outer circle, and then we subtract the area of the inner circle, then we can just add all of those washers instead of this together, then we'll be able to get a volume. So when we have this rotated around x equals -4, the distance is going to be 4 minus -4, so it's going to be 8. It's 8 units. X equals 4 is 8 units away from x equals -4. And then this is pi times 8 squared minus 1/2 y plus 7/2 squared. When you add 4 to this, 1/2 y minus 1/2 plus 4, you get 1/2 y minus 7/2. And yeah, I mean, from here, this is again y, because y will be constantly changing as you have that washer right there, and it goes like that. The values of y, as they change, the actual inner radius will be changing as well. The outer radius will stay 8 for as long as we are rotating it, but the inner radius will change for different values of y. So yeah, let's just expand this. We have 64. Well, this is also going to be multiplied by pi because it's also the area of a circle. So we have 64 pi minus pi over 2 y. Oh, I need to actually expand things correctly. Y squared over 4 times pi plus 7 over 2 times y minus, oh, this is actually going to be minus as well. Whoops. Minus 7 over 2y, and then minus, let's even put a pi out in front, minus, what's it going to be, 49 over 4. So this is equal to 256 over 4 minus 49, that's going to be 207 over 4. So we're going to have positive 207 over 4. So let's rewrite what we have. We can put that negative back inside. So we're going to have positive 207 over 4. And all of this will be multiplied by pi. And so from here we just integrate. And our bounds are from the base, the base y value, which is y equals 3, up to y equals 9. If you again think about that like solid, the height will be within the bounds of 3 to 9. So let's do the definite integral of this bad boy from 3 to 9. So let's integrate this normally. We'll do pi 3 to 9. And so I know I'm working in the complete opposite direction, but we are rebellious. We have y to the power of 2, so 1 over n plus 1 is going to be 1 over 3, and then 2 plus 1 is going to be 3, so we have 1 over 3 times 4, negative 1 over 12, y to the 3, minus 7 over y to the 1 plus 1, so 2. 1 over 2 is going to be, 1 over 2 times 1 over 2 is going to be 4, so we have 7 over 4y squared plus 207 over 4y, derivative of the antiderivative of 1 with respect to y is going to be y, so derivative of 207 over 4 with respect to y is going to be 207 over 4y, and let's just plug this in, and then actually I'm just going to keep the pi outside so I see what the actual constant value is. 207, oh, and I forgot the bounds. This is going to take me a little while to plug in my calculator. feel like it's just kind of awkward silence. Um, so, how was your day? No, that was dumb. Um, Mine was very interesting. I finished applying to college, well, to most of my colleges, and I know I should be, you know, happy or something, but I'm just apprehensive. That's probably the best way to put all of it. But we thrive in apprehensive situations. That's that doesn't make any sense. But I'm getting through it. There's not much to get through, but And 207 over 4 times 3. Alright, 126. We got 126. We could maybe actually do this correctly. Because, we have 729 over 12 minus 568 over 4. You can multiply 568 by 3 and then, do some stuff. Actually, 568, negative 568 plus 207. You could, do this by hand, and it wouldn't be too much of an inconvenience, but, we're already a little bit behind track. This is 126 pi. That is the volume of this solid. And I might do some, practice of these. I don't really want to think about that because I'm honestly getting a little bit sick of these integrals. But, this is important, even though I truly, truly dislike these kinds of problems. Volume of solids of revolution, easily my least favorite integration topic. But, let's get into some of the more interesting stuff. I have a worksheet that I want to complete, and that is some integration by parts. So we're going to have the integral of x sine x with respect to x. So what is easier to differentiate? Again, just to review integration by parts, we're going to try an undo product rule. So, not undo product rule, but you have a product of a function and you are trying to undo that product. So we have the integral of x sine x dx. You want u. So let's even write down what the integration by parts formula is. It is the integral of u with respect to v is equal to uv minus the integral of v with respect to u. So what's the integral of, you want u to be easy to differentiate, so that du is nice and simple and you don't have to change v too much, and you want v to be easy to integrate, so that, it's obvious you have to do the integral of v at some point, so you want it to be relatively easy. So what's easier to differentiate between x and sine x? I'd argue that x is easy to integrate, so let's let u equal x, and then du dx will be equal to 1, so du is just going to be dx, and then dv will be equal to sine x dx, which means that v will be the antiderivative. If the derivative of sine is cosine, then the antiderivative of sine will be negative cosine. Or, I messed that up. The derivative of cosine is negative sine, so the antiderivative of positive sine is going to be negative cosine. So negative cosine x. And, let's just plug this in. We have x times negative cosine x minus the integral of v, so cosine x will make that negative to a positive, dx. And this is just going to be what we just said, that the derivative of sine is cosine x, so the antiderivative of cosine x is going to be sine x plus sine x plus c. Right, that was relatively okay. So let's get into another one. We have x cosine 4x. Okay. Again, I'd argue that it's most likely easier to differentiate x than it is to differentiate cosine 4x, just because I think that 1 is a lot simpler to work with than, what you would get with differentiating cosine 4x. So let's let u equal x, du will again be dx because u dx is equal to 1. Then dv will be cosine 4x dx. So let's do u sub. We have, well, I know we're working with u, but this is just to integrate this. U will equal 4x, so du dx will equal 4, which means du is equal to 4 dx, which means that dx is equal to du over 4. So the integral of cosine u over 4, so we can bring that 1 over 4 out, du. So this will be 1/4 sine du, or 1/4 sine 4x. Okay, so v is equal to 1/4 sine 4x. So uv will be 1/4 x sine 4x, and then minus v du. So this will be, we can bring that 1/4 out. Integral of sine 4x with respect to x. And then this one's another another relatively simple u sub. We're going to have u is equal to 4x again, du dx will equal 4, so du is equal to 4 dx. So that means that dx is equal to du over 4, so we plug that in. We have sine u, well, we can bring that 1/4 out again, sine u du. And then we have, if the derivative of cosine is negative sine, then the antiderivative of positive sine is going to be negative cosine. So we have 1/4 negative cosine, well, times negative cosine 4x. So that 1/4 times 1/4 is going to be 1/16, and then that negative will make this into a positive. So not there. It will be 1/4 x sine 4x plus 1 over 16 times cosine 4x plus c. So I'm hoping you start to see that this pattern, while it might seem, a little bit kind of annoying, but it is a rhythm. Once you get into it, it definitely does just kind of fly by. Once you get into that rhythm of just solving, and solving, you'll just fully understand it at a certain point. So let's do another one. We have quite a few more. We have the integral of x to the x times e to the negative x with respect to x. So which of these is easier to integrate? Well, which one's easier to differentiate? Let's start with that. We'll have u is equal to x, which means that du is equal to dx. Whenever you have x as one of your potential, well, if you have x as one of the terms in this product, then it's most likely going to be x that you are differentiating. But, du is equal to dx because du dx is equal to 1. That means that we are trying to integrate dv is equal to e to the negative x dx, which means that u will equal negative x for this u sub. Du is going to be negative dx. So, that's because du dx is equal to negative 1. And then we just do u sub, so we can factor out that negative. We will have, hold on one second, we'll have negative e to the u du, which is going to be just e to the u. So we have negative e to the negative x, and so v is equal to negative e to the negative x, which means that uv is going to be negative x times e to the negative x minus v du. So we have a minus already in the v, so we're going to make that a plus e to the negative x dx. And since we just did that, we know that this is equal to negative e to the negative x. So we have negative x times e to the negative x minus e to the negative x plus c. Okay? So, I'm not going to pretend that this is easy or anything, but once you get into that rhythm, once you see this is what I need to differentiate it, this is what I need to integrate, then these will just kind of fall in line. You'll just start to just see these, which is definitely a fun experience. So let's do integral of x squared cosine x. This one I'm going to do tabular method dx. So tabular method I'm going to use. I use tabular method relatively sparingly. I understand that it works. I know kind of why it works, and like, it's not that I think it's bad or anything, but you can definitely. I feel like integration by parts just makes more sense if you use the formula, but tabular method is obviously very good. And I think tabular method works especially well when you have one of these cycling functions. I did talk about this a little while ago, but sine x, that derivative is cosine x, the derivative of cosine x is negative sine x, derivative of negative sine x will be negative cosine x, and then the derivative of negative cosine x is negative negative sine x, so that will be positive sine x. And then this cycle will just continue to happen. So if you just constantly integrate, so if we go in this direction instead of that direction, then it'll just continue to cycle as well. But if you have a function that will definitely go down, like once you continually differentiate it, if you have like x to the power of 3, that will eventually go to 0 after you differentiate it enough times. So I like using tabular method for this because it's just an easier way of showing my work. But yeah, let's let u equals x squared, because I know for a fact that since this follows the like a power rule, eventually after doing enough differentiations you will get to 0, and you let v equal cosine x. This will constantly, let's keep our signs, this will constantly integrate to the same cycle. So we have sine plus minus, again, with that integral of u dv equals uv minus the integral of v du. This is plus and this is minus, so let's just differentiate this. We have u equals x squared, so u equals x squared, v equals cosine x, and then you'll have 2x. You bring that 2 out, and then 2 minus 1 is 1, so you'll have 2x. The derivative of sine x is cosine x, so the antiderivative of cosine x is going to be sine x. And then derivative of 2x is 2. Antiderivative of sine x, well, we know that the derivative of cosine x is negative sine x, so the antiderivative of positive sine x is going to be negative cosine x. And then derivative of a constant is 0, and then antiderivative of negative cosine x will be negative sine x. Okay, and we want to have u times v. So if this is dv, right, this is the already differentiated v, because we have u dv, then you have to multiply across this diagonal to get uv. It's not supposed to be u, that's supposed to be v, and this is supposed to be u. Then you have to do minus v du, so minus v du, and plus uv minus, well, 0 times anything will be 0, so we don't actually have to do that one, but let's just put down everything that we have together. We have x squared sine x minus 2x times negative cosine x, so plus 2x cosine x, plus 2 times negative sine x, so minus 2 sine x, plus c. So yeah, I mean, not the biggest fan of tabular method most of the time, but it definitely does have its merits, especially when you have like a cosine or a sine or some type of trig function that just integrates really nicely, and another function that's multiplied to that that you know will eventually differentiate to 0. So let's go into the next one. This is another one that you might want to use tabular method on, because even though it doesn't cycle, e to the x is a very nice function to integrate. So we have 2x squared e to the x dx. So I know that 2x squared will eventually differentiate down to 0, and e to the power of x integrates really, really nicely, so I don't need to do too much there. So let's do sines plus minus, and then u can equal 2x squared, and then v will equal e to the x. So u 2x squared, 4x, 4, 0. I'm kind of just going through these, but if n is equal to 2, 2 times 2 is 4, 2 minus 1 is 1, and then, just on from there. Integral of e to the power of x is e to the power of x, so that just stays the same. Like that, again, this is why Avogadro method is really nice for these like functions that either cycle or just integrate very nicely. So we multiply across this diagonal and then multiply the sign, so it'll look like that. So we'll have 2x squared e to the power of x minus 4x e to the power of x plus 4 times e to the power of x plus c. So, yep, we did that. Now we have an interesting looking one. Definitely possible, by the way, just interesting. So we have x squared ln x dx, and this is in absolute value. So which of these is easier to integrate or easier to differentiate? I think this is definitely easier to integrate. Easier to differentiate because we know that this one is just going to be du dx will equal ln x, so du is going to be equal to 1 over x dx. And then dv, even though x squared isn't the easiest function to integrate, we do know that 1 over 2 plus 1 will be 1/3, and then 2 plus 1 will be 3, so we have 1/3 x cubed. So let's do uv. We'll have, well, this will be absolute value as well, 1/3 x cubed ln absolute value of x minus v du. So we're going to have that 1/3, we'll bring it out, x cubed du, so x cubed over x dx. So we're going to make the x squared 1/3 x cubed ln absolute value of x minus 1/3 x squared dx. So 1 over 2 plus 1. Again, we did this. Well, I'm actually not going to show it work because we just did this antiderivative right there. So we're going to have 1/3 x cubed ln absolute value of x minus 1 over 3 times 1 over 3. So 1 over 9 x cubed plus c. Okay. We're just kind of busting through these. I mean, like, at a certain level, I think it comes down to seeing that pattern, just seeing which needs to be differentiated, which needs to be integrated, and then just like a machine, plugging it back into your formula over and over again until you get the answer. Integration by parts, it is definitely intimidating, but I'm hoping that just by like brute forcing as much integration as I can into this video, I'm hoping you can see that integration is honestly not as bad as it might seem. It is work, it is a lot of it, but it's definitely possible. It's definitely possible. So we have another interesting one. We have the integral of arctan x, or the inverse of tan. So with functions like these, we might just say, oh, this is one function, so there's no way that we can do product rule, or there's no way that we can do integration by parts because there isn't a product of two functions. But when you have this one that appears to be by itself, you also need to remember that this is arctan times 1, right? Arctan times 1 is arctan, and anything times itself is going to be itself. Oh, anything times 1 will be itself. So we know that u will equal, it's not going to be 1. Even though 1 is very easy to differentiate, you'll just get 0. Your final answer will be nowhere close because, how? Like, you just get 0. If you have uv, which would be 0 times whatever v would be, minus v du, so 0 du, you just get 0. So that's definitely not going to happen. I think there's probably a more formal way of describing why it doesn't work. But, u will definitely be arctan. And we know this differentiates rather nicely. We talked about this earlier. Du dx will be 1 over 1 plus x squared. So 1 plus, I wrote it wrong, du will equal dx over x squared plus 1. And then we will let dv equal 1 dx, which means that v will be just x. So we have uv, so x arctan x, minus, we can do some interesting stuff. So let's do our uv. We have, or our v du, we have the integral of x squared plus 1 dx. Now, this is obviously kind of difficult to work with. I know that much. But we can do u sub for this. I know we've been doing a lot of stuff with u, but we can do u sub for this. And so if you do u is equal to x squared plus 1, u equals x squared plus question mark, u equals x squared plus 1, and you do du dx, you'll get du is equal to 2x dx, because du dx is equal to 2x. Then when you solve for dx, you'll just get du over 2x. So this will cancel out, x and x, and you bring that 1 over 2, and you're just going to be left with 1 over u du. And so this integrates very nicely to ln of u. So you have x tan, or arctan x, minus 1/2 ln of the absolute value of u, which we said was x squared plus 1, plus c. Okay. What else do we have? Oh, another rather fun one. We have arc sine x. So, same methodology. Let's arc sine x. We have arc sine x is equal to arc sine x times 1. So u will be arc sine x, which we said the derivative of arc sine x, so du dx, will be equal to square root of 1 minus the square 1 over the square root of 1 minus x squared. But since we're solving for du, we'd have dx over the square root of 1 minus x squared. And then dv will equal 1 dx. So we'll be left with x. V will equal x. And so uv, x arc sine x, minus v du, minus v du. So we have x over square root of 1 minus x squared dx. So again, let's do some u sub. We'll say that u is equal to 1 minus x squared. It's a function inside of a function. Du will equal negative 2x dx. Well, because du dx is equal to negative 2x, derivative of the constant 0, so derivative of 1 is 0. So du will equal negative 2x dx. And yeah, from here, we can solve for dx. We'll get du is equal to negative 2x, or du over negative 2x. Then x and x will cancel. We can bring that negative 1/2 out here, so it'll be plus 1/2. And then we have 1 over square root of u times du. So we'll have x arc sine x plus 1/2 times this integral of 1 over square root of u. We'll even write that as square root of u is 1 u to the power of 1/2, and then negative, so that'll be 0 u to the negative 1/2. And so when you do 1 over negative 1/2 plus 1, you'll get 1 over 1/2, which is 2, times u to the negative 1/2 plus 1, so u to the 1/2. Those 2's will cancel out. Let's just put an imaginary 2 up there. And then you'll have u to the power of 1/2. So we'll have x arc sine x plus u, or the square root of u, which is going to be square root of 1 minus x squared plus c. Okay, next practice problem. This is one of the best examples of why you should not be using tabular method unless for everything, unless you have like a very like intuitive sense of when you should stop. So it is e to the power of x times cosine x dx. For this one, I would not use tabular method because both ex and cosine x cycle. When you differentiate e to the power of x, you just keep on differentiating, you will never get to 0. And if you keep on integrating cosine x, you will just eventually come back to cosine x. And that goes double for e to the power of x. If you integrate e to the power of x over and over, you will get e to the power of x. And if you differentiate cosine x over and over, you will eventually get back to cosine x. So unless you know when to stop differentiating and integrating, you will just keep on doing that forever. So it does require some, I wouldn't say super critical thinking or anything. Like, you can definitely do it. It's not impossible or anything, but I would probably stay away from, doing that. But yeah, let's just get into this problem. We have I'll let u equal e to the power of x because I know that this is very nice. Du equals e to the power of x dx, and then dv will equal cosine x dx, which means that v will equal sine x. Derivative of sine is cosine, so antiderivative of cosine has to be sine. So we'll have e to the power of x sine x minus v du. So we're going to have the integral of sine x, or e to the power of x sine x dx. Let's let u equal e to the x again. Du will equal e to the x dx. And then dv, that will be sine x dx. And then v, if the derivative of cosine is negative sine, then the antiderivative of positive sine is going to be negative cosine. So this will be a positive. We'll have e to the x sine x plus the integral. I need to just say integral over and over again. I keep saying interval, but integral of v du, so e to the x cosine x. Oops, forgot something. Oh yeah, you have to do uv. So this has to be e to the power of x sine x minus uv minus that. So let's think about this. We'll have plus, so minus uv will be plus e to the power of x cosine x, and then minus v du, so plus e to the power of x cosine x dx. And this is equal to that. So let's just say that I is equal to this, and I is also equal to that. So you have I equals e to the power of x sine x plus e to the power of x cosine x plus I. Wait, what? Let me think. Something went wrong. Oh, this is 3 negatives. You have uv minus v du, that negative. You have the negative cosine negative, and then you just have this distributed negative. So this will be negative times negative, which is negative. So this will be minus I, and then you can add I to both sides. I was like, no, I would just cease to exist. But you have 2 i's equal to that, and then let's even write that down. 2i is equal to all of that. And then you just solve for I. You get I is equal to 1/2 e to the power of x times sine x plus cosine x plus c. So that's how you would do that one. And then we have sine x cubed. the integral of sine x cubed. So let's write that down. And then this will probably, we do have some definite integral practice, but this will be one of the last integration by parts ones. I'm hoping that you are just like, now that pattern is becoming slowly, a little bit by bit, just second nature. You see, u needs to be differentiated, v has to be integrated, u has to be easy to differentiate, v has to be easy to integrate, and you just need to see that pattern. You need to see when these functions will approach 0 after being differentiated enough times to see whether you can use tabular method or not. You need to see whether these will cycle, whether you're going to have to do that I method that I just talked about, or whether you're going to have to do normal integration by parts. But let's do one last indefinite integral example. So we have sine cubed x dx. So sine cubed x, you might think that we could use chain rule, but if you do it, you'll get like a cosine thing times a sine thing, which is definitely not going to cancel out nicely. So we're going to have to do sine x times sine squared x. This is another thing that you can do with these products of two different functions. You just have to split them. Well, not with the product. You have to make it into a product. If you have a singular function that can't be u-subbed correctly, just write it as the product of two separate functions and then see if you can do integration by parts. But yeah, let's let what be what? Let's let sine squared x be equal to u. Yeah, I think I made the correct choice. It would be a lot more difficult to do this one, but let's do sine x squared. This will be chain rule. So f prime g of x times g prime x. G prime x will be cosine x. And then f prime will be 2 sine x. I think that's fine. Let me just check. Okay, yep, that seems fine. So du will be 2 sine x cosine x. And then let's let dv equal sine x dx. And we know that by now this will just be v is equal to negative cosine x. So let's write down all that good stuff. We have negative sine squared x cosine x minus u or v du. So yeah, minus v du. So it's gonna be plus cosine. Oh, wow, this is gonna be not the nicest looking derivative or integral. So plus v du, or plus cosine squared, well, let's bring that 2 out, cosine squared sine x. So we have cosine squared x. Cosine squared of sine x would be a much more difficult integral to calculate, but we have a function inside of a function, cosine x, instead of a larger f of x squared. So let's let u equal cosine x du can equal negative sine x dx. And then dx will be du over sine x, negative du. And so this will cancel out, this will cancel out, and then you'll just get u squared. So yeah, and we can just bring that minus out, so we have minus u squared du, and then that will just be negative 2 over 3 u to the 3. So our final answer is just going to be negative sine squared x cosine x plus, or well, minus 2/3 minus 2/3 cosine cubed x, and then plus c. So, yep, that's all well and good. Now let's go into some of the definite integral examples that they gave. Again, definite integrals are just indefinite integrals that are defined. So, I mean, once you understand the antiderivatives and you can just do them, definite integrals are not anything to be afraid of. So, let's just do a couple for practice. We have the integral from 0 to pi of x cosine 1/2 x. Ooh, fancy. But, you know, it's definitely within our realm. We have u is equal to x, which means that du has to equal dx because du dx is equal to 1, solve for du. And then that means that dv is equal to 1/2, or cosine 1/2 x dx, which means that we have to do u sub. U is equal to 1/2 x, du is equal to 1/2 dx, and then dx is equal to 2 du, which means that you bring out that 2, you have 2 times cosine u du, and that's going to be 2 sine u, which is 1/2 x. So we have 2 sine 1/2 x, v is equal to 2 sine 1/2 x, and then we do all that fun stuff. We have 2x sine x, or 2x sine 1/2 x, so uv minus v du. We bring out that 2, we have sine 1/2 x dx. And when we have this integration by parts, we actually have to plug in pi and 0 for that, because we integrated v, and we have to use the same bounds that we integrated with for the other ones. So we also have to do pi and from 0 to pi for this uv, as well as this v du. And then this one, it's the same process. U is equal to 1/2 x, so dx will equal 2 du. But instead of that, we're going to have sine u, which will be negative cosine u. So we'll have negative 2 sine cosine u. So negative 2 cosine 1/2 pi, 1/2 x. So let's see if that makes sense. Cosine, yep, negative sine. Yeah, no, that seems fine. Wait, what? Yeah, since this will be plus because we're already given a minus. So, yeah, let's just plug in pi and 0. I am not of the mental fortitude to try and actually solve this. So we have 2 pi minus sine pi over 2. Pi, just pi over 2, yeah. Sine pi over 2. So we're going to have 2 pi. That's what this will evaluate to. Okay. That's not good. Oh, here it is. We have 2 pi is what this whole thing evaluates to. And then we had to do plus 4 cosine 1/2 x. Let's really quickly just make sure that we did this correctly. We have cosine 1/2 x, chain rule, since 1/2 x is an inside function. Derivative of 1/2 x is going to be 1/2 times the outside, so 4 will be 2 times derivative of the outside, which was cosine, so negative sine. So, yep, negative 2 sine 1/2. I just had to make sure of that myself. And then we plug in our bounds, which are from 0 to pi. So, let's do that real quick. Minus 4. So, and cosine of 0 is going to be just a 0. So we have Oh, no, cosine of 0 is not 0. Cosine of 0 is 1. So we have 2 pi minus 4. That's our first one. And then let's get into a couple other examples. I think I'm only going to do like 2 or 3 more of these definite integrals because it's just a regular integral but with definition. So let's do the hard ones. We have the integral from 1 to 2. I mean, this one's not too bad, but the integral from 1 to 2 of x cubed ln x dx. Actually, this might be a little bit challenging. I wouldn't use tabular integration for this either because though you can integrate this real nice for, though you can differentiate this really nicely for the first one, 1 over x, when you keep on differentiating, you will never get to 0 because you'll have negative exponents, and those negative exponents will continue to decrease. And when you integrate x cubed, you will have positive exponents that continue to increase. So you will actually never end. I think that the regular integration by parts is probably a little bit better for this one. So which of these is easier to differentiate? Well, again, matter of preference. I think probably for our case, ln will be easier to differentiate, so we'll let u equal ln x, which means that du is equal to dx over x. That means that dv is equal to x cubed dx, which means that v is equal to 1 over 3 plus 1, 1/4, times x to the 3 plus 1, x to the power 4. So we have uv, 1/4 x to the power 4, ln, absolute value of x, and these bounds of 1 to 2 still apply, minus v du, so we're going to have 1/4, we can pull that out, integral x to the power 4 over x dx, right? And yep, and this is also from 1 to 2. And let's see if I did that correctly. Great. And so let's plug in the values. I probably could do this one actually, but again, very lazy. Actually, I'm not as lazy as I think I am. ln of 1 is going to be 0, so I already know that there's no second term. So 2 to the power 4 is 16, divided by 4 is 4, and then ln of 2 is going to be remaining as ln of 2. So 4 ln absolute value of 2 minus 1/4 of the integral of x cubed from 1 to 2 dx. So you're going to have, no, whoops. I don't think I'm wrong. Maybe if I integrate not integrate not as an integrate, but like maybe if I reincorporate the minus 1/2 back in and then just flip the arctan and the x, then you'd get pi over 4 minus 1, so negative, no, that doesn't work. It's 3 pi over 8. Yeah, I don't know, I'm doing something wrong. But I integrated it correctly. At least I think I did. I wouldn't know where I made a mistake, though. Let me think. Minus 1/2 plus power 8. Yeah, I don't know. Interesting. Well, you know, I'm lazy, so I'm going to let somebody in the comments, if they manage to make it all the way over here, if they manage to make it all the way over here, I want them to tell me exactly what I did wrong, because I don't know. I'm like pretty sure. Like, I wouldn't say super sure or anything, but I'm like pretty sure I got the correct like integral. Maybe I was being a little bit too ambitious in trying to do that on my head, but I'm pretty sure I got the antiderivative correctly. But I'm tired, so let's go into partial fraction decomposition. I did talk about this a little while ago, but we do need to, go through it a little bit. Let's see, which one should we start with? So, let's do the integral of 1 over x plus 2 times x minus 1 dx. So x plus 2 times x minus 1 is obviously a product of two binomial terms. So if you find a over x plus 2 plus b over x minus 1, if you have the least common multiple, then sum a times x minus 1 and this b times x plus 2 will equal 1 over x plus 2 times x minus 1, because we can't actually simplify this any further. We have to do partial fraction decomposition for this one because we can't simplify this any further, and there is no easy way to integrate this. So yeah, we have this format. We have a times x minus 1 over x plus 2 times x minus 1 plus b times x minus 2, or x plus 2, all over x plus 2 times x minus 1 is equal to 1 over x plus 2 times x minus 1. Alright? And then we have ax minus a plus bx plus 2b is equal to 1. So a plus b is equal to 0 because there's no term with an x attached to it in this side of the equation. A plus b equals 0, and then negative a plus 2b equals 1. So we have, when we add them up together, we will get, let's see. No, I think this is fine. Something's up. Oh, got the wrong thing. This is plus, so we have ax plus a. So yeah, when we subtract this, we'll get a negative b equals minus 1, so b is just equal to positive 1. Negative b is equal to negative 1 when you subtract a and 2b from a and b, and 1 from 0, so b is equal to positive 1. Then we plug that back into a plus b is equal to 0, which means that a is equal to negative 1. This is just the systems of equations way of solving this. There's obviously going to be a perhaps slightly better way of solving this for people who want to solve things with a higher degree quotient. So yeah, we have, let's write this down, we have 1, or negative 1 over x plus 2 and then positive 1 over x minus 1. So let's do some u sub. This is obviously integrated with respect to x. So when we do some u sub, we're going to have to, well, I don't think u sub is necessary for these ones because you'll see a pattern here very quickly. If u is equal to x plus 2, then you do du equals dx. And then when you substitute this in, you'll get 1 over u times du. Du is equal to dx, so you just plug it straight in. And then if u is equal to x minus 1, then du will equal dx. So you'll have 1 over u and du again. So when you have these terms where x is not multiplied by any factor, it's just x plus something or x minus something, you just have ln of that something. So this will be minus 1 half, or not minus 1 half. This will be, whoa. Don't know what happened here. Let's try and get back on track. Oops. Come on. There we go. There we go. We have minus ln of x plus 2, absolute value of x plus 2, plus ln of x minus 1. because we had 1 over u du for both of those, and u was equal to x plus 2 and x minus 1 respectively, and the integral of 1 over u with respect to u is just going to be ln of u, absolute value, plus c, and that's just going to be the pattern that we are going to follow. So let's do some more crazy looking ones. We have, I'll do the, like, I wouldn't say, it's probably better. I'll just do the way that you're supposed to do it in a little bit, but I like my systems of equations. I think it's fun, because I'm a nerd, but, you know, just in general, I think systems of equations are pretty fun, outside of, you know, the context of being forced to do them for classes. I think that they're just interesting. It kind of reminds me of like a jigsaw puzzle, but with math. So we have a over 2x minus 3 plus b over x minus 4 is equal to sum x over 2x plus 3, or 2x plus 3 x minus 4, 2x plus 3 x minus 4. I keep making that mistake. 2x plus 3 times x minus 4, and then a times x minus 4 and b times 2x plus 3. So we'll have a x minus 4 plus b times 2x plus 3, and they will both be over, you know, 2x plus 3, x minus 4, and then this will also be over 2x plus 3 times x minus 4, and this will equal x over 2x plus 3 times x minus 4. And since they have the same denominator, we can just cancel them all out, and we'll get ax minus 4a plus 2bx plus 3b is equal to x, which means that a plus 2b is equal to 1, and then negative 4a plus 3b, I don't know why I put bb, but plus 3b is equal to 0. There is no term, there is no constant on the right hand side of the equation, and so from here we can do a myriad of things. I'm going to just multiply everything by 4, so that'll be 4 plus 8 plus 4, and then we add them, so we'll get 11 over 4. So, 11b is equal to 4a, which means that b is equal to 4 over 11. And let's plug. Wow, that's a weird one. So 4 over 11, and then we had an original a plus 2b is equal to 1. Not 11. A plus 2b is equal to 1. And so 4 over 11 times 2 is going to be 8 over 11. 1 minus 8 over 11? That doesn't sound right. Hold on. Let's see. A plus 2b does equal 1. 4 over 11. I don't know. I think oh. Wait. What? No. Let's just plug it into the other one. Negative 4a plus 12 over 11. So negative 12 over 11 divided by 4. That's going to be 3 over 22. That doesn't sound right either. Yeah, no, not sure if that makes too much sense. Oh. No, I get it. So, a is just going to be equal to 3 over 11, right? Because if b is equal to 411, then 2b will be 8 over 11, and then 1 minus 8 over 11 is just going to be 3 over 11, so a will be equal to 3 over 11. So let's rewrite this. We will have we can actually just pull those fractions out so that they're a little bit easier to work with. We'll just have 3 over 11 times 1 over 2x plus 3 dx plus the integral of 1 over x minus 4 dx, well, times 4 over 11. And automatically, I'm going to have to break that rule that we just established, because 2x plus 3, if you do u sub, you get u equals 2x plus 3. You get du is equal to 2 dx, which means that dx is equal to du over 2. And so we'll have to pull that 1/2, so we'll get 3 over 22 is equal to 1 over u du. So 3 over 22, integral of 1 over u du, we said that that's ln of u, so let's write that down. We'll have the ln of u, which we just said was 2x plus 3, so ln absolute value of 2x plus 3, and this rule does work for this one. So if the x is by itself, it does not have a coefficient or has a coefficient of 1, then we can do that like idea, and we'll have 4 over 11 times ln x minus 4. If you have a coefficient other than 1, it could be a fraction, it could be a number. If you have a coefficient other than 1, when you do u sub, you will have a du that is different from your dx, so that trick does not work. And then we have plus c. So yeah, that was another example in the bag. I'm getting very tired if it's not obvious, but we can keep going, you know. It's technically not a school night, so we have all the time in the world. Not exactly, but we do have quite a bit of time, so let's do another one. We have 3x plus 2 over x minus 1 and x plus 7. So a over x minus 1 plus b over x plus 7 equals 3x plus 2 over x minus 1 times x plus 7. And I'm gonna assume that you guys see the pattern, so I'm not gonna rewrite that all over again. We have ax plus 7a. You multiply a by the term that it's not attached to, plus bx minus b is equal to 3x plus 2, a, bx, 3, those are the things that correspond with x. We have a plus b is equal to 3, and then 7a minus b is equal to 2. So when we add the two together, you'll get AA is equal to 5, which means that A is equal to 5 over 8. And then B will be 3 minus 5 over 8, so 24, 19 over 8. And so let's just factor that out. We will get, real quick, we will get A, which is 5 over 8, outside of this integral of 1 over x minus 1 dx, plus 19 over 8 factored out of this integral of 1 over x plus 7 dx. And then from here, our ln rule does work, so we don't have to, do u sub. I mean, technically we're doing u sub, we're just skipping the work for it, because, I mean, if you do u sub of x minus 1 or x plus 7, you'll get du equals dx, and you'll just get 1 over u, so we'll have 5 over 8 ln x minus 1 plus 19 over 8 ln x plus 7 plus c. Alright, now we get into some of the more interesting ones. We have 1 over x plus 3 cubed times x minus 1. Now for these ones, when you have a repeated root in the denominator and you have to do this differentiation or this integration, you have to actually include both the repeated root itself and all of the roots that has been repeated so far. So with 1 over x plus 3 cubed times x minus 1, we're going to have to do a over x plus 3 squared plus b over x plus 3. So both the repeated root itself and the roots that have been repeated. plus c over x minus 1 to get 1 over x plus 3 squared times x minus 1. And that multiplication is still the same. You're going to have a times x plus 3 times x minus 1 plus b times x plus 3 squared times x minus 1, and then c, which you are going to just get x plus 3 cubed, is equal to 1. Now for this one you have to plug in factors that zero out the others. So if I want to isolate this c, I notice that x minus 1 is not common to it. So if I have a number that makes x minus 1 equal 0, 0 times b will equal 0, and 0 times a will equal 0. But whatever number that I plugged in will leave me with a tangible c that I can calculate for. And that number is going to be 1. You want x minus 1 to equal 0, so if you add 1 to both sides, you'll get x equals 1. So let's plug in x equals 1, and we will get a times 1 plus 1. I'm not going to show the work for the ones that 1 minus 1 is in there for, because 1 minus 1 is 0, and anything times 0 is 0, so a times 0 is 0, plus b times 0 is 0, plus c times 1 plus 3 cubed. Let's see, c times 1 plus 3 cubed? Huh. Wait, does that make sense? Oh. Wait, no. that's unnecessary, because the, that's unnecessary because the x plus 3 was already accounted for in x plus 3 squared, right? Because x plus 3 is still common to x plus 3. There's no, the least common multiple between x plus 3 and x plus 3 squared is still x plus 3 squared. So I didn't need to do that. We're just going to have a much less temperamental 1 plus 3 squared. So we're going to have c times 1 plus 3 squared is equal to 1. That does not change when you plug in x equals 1, which means that c is equal to 16c is equal to 1, which means that c is equal to 1 over 16. Then let's plug in negative 3, because that's the other factor that zeroes out. If you plug in negative 3, well, let's attempt to plug in negative 3. That's another number that zeroes out, but it zeroes out every single term, so it's not going to work out for this one. We have to do something different, and this one we actually do need to use our system of equation method. We have x equals 1 was the zeroing factor, and negative 3 is the zeroing factor. So we have to come up with numbers in and around that range of values that we can plug into this equation to get a system of equations that we can solve a and b for. So let's use x equals 0. That's also relatively close to both 1 and the negative 3. So x equals 0. And so when you plug that in, you'll get a times 0 plus 3, so 3a times negative 1 plus b times 3 squared times negative 1 plus c times, b times 2 plus 3, so 5 squared, so 25 times 1 as well, plus c times 25, so 1 over 16 times 25 is equal to 1, which means that we have 5a plus 25b is equal to 16 over 16 minus 25 over 16, so negative 9 over 16. Oh wow, this is definitely gonna not be the greatest one. I'm actually probably gonna just plug this into my calculator and see if we get something. I'm just gonna multiply the all the terms in the first equation by 5. So you have negative 15, negative 9 times 5, so negative 45. What's 7 divided by 16 times 5? Okay, we'll keep that. And then we have everything in the second term multiplied by 3. So we'll have 25 times 3, 75. I don't know why I was about to try and calculate that. And then negative 9 over 16 times 5. Okay. Oh, never mind. I thought that these were the exact same one, but 2.1875 and 2.8125 are different. And so we do negative 15 plus 15 to get 0. And then we had negative 45 plus 75. I don't know why I'm writing this out. I know it's 30. But 30 is equal to 2 over 16, well, 7 over 16 times 5 plus, minus 9 over 16 times 5. So that's going to be like, I don't know, maybe, let's see, 2.1875. I have to actually type this out like a peasant. If only I could store my answers efficiently. Minus 0.625 divided by 30. Ugh, what? Yeah, no, something went egregiously wrong here. I don't know though. Like, I know that 1 over 16 for C is correct. Like, I know that for a fact. But, 25 over 16. Did I do 1 minus 25 over 16 incorrectly? Yeah, I did. Oh my god. What? Wait. What? Let's do it. 16 minus 25 divided by 16. What? Okay. Must have inputted something. Oh. Ugh, this calculator's stupid. Okay. No, I think we're fine. Let me do this one last time. We have this times 5. Okay. That seems okay. And then this. Wait, what? What? Yeah, no, I don't know. 25 to. That's correct, right? 5a, 25, negative 9 over 16. That's 5a plus 25b equals negative 9 over 16. That's correct. I know that is. And then when we plugged in 0, we had 3, 9, 1 minus 9 over 16. That's, yeah, no, that's 7 over 16. Well, you know, we all make mistakes at some point, and I've made several over the course of this very, very long video. But I honestly don't know what I've done incorrectly. Because maybe there's something wrong with how I plugged everything in. Let me try this one more time. Negative 15, negative 45, plus 75. Oh, God, I'm dumb. Yeah, it's negative 9 over 16 times 3. It's not negative 9 over 16 times 5. So this is plus 7 over 16. Yeah, and then this is divided by 30. Okay, perfect. Yep. Well, is it perfect? Dun, dun, dun. Hold on 1 second. We did that times 5. That times this. So this plus 7 over 16 times 5. Oh. Yeah, no. That's annoying. Okay. Now is it right? Okay, whatever. Whatever. even when I'm plugging things into a calculator, I don't know what I'm doing. This systems is correct. I'm pretty sure about that, but I just didn't solve for B correctly. B is going to be, after all of that, should be, uh, let's see, negative 1 over 16. Then we plug that back into your calculator. I'll just save you the trouble. 9 over 16, 7 over 16 minus 9 over 16 is negative 2 over 16, and then divided by 3. Wait, what? Huh. Oh, wait. No. Yeah, something wrong with my systems. Uh, I guess I'm just gonna skip this, but, you know, it's good practice to at least integrate this properly. We did get C over 16, right? So that's a point in my book. Um, Apparently the correct answer, at least on the back of this worksheet that I've been looking at, the correct answer is supposed to be the fractions of negative 1 over 4 times 1 over x plus 3 squared. So a is equal to negative 1 over 4 plus, or minus 1 over 16 times 1 over x plus 3 plus 1 over 16 times 1 over x minus 1. We didn't get this part correct, but something wonky happened with this part, and well, we can still try and integrate this properly. All of this is integrated with respect to x, of course, and then we have u is equal to x plus 3, du is equal to dx. So we're going to have u to the negative half, negative 2 du. When we do that integral, plus 1 over negative 2 plus 1, so we're going to have just negative u to the negative 1. So we're going to have positive 1/4 times u, or x plus 3 to the negative 1. So 1 over x plus 3 minus 1 over 16. We can still do that ln trick because u of x plus 3 du, that's just going to be dx, and if u is x minus 1, dx will also be du. So ln x plus 3 plus 1 over 16 ln x minus 1. Alright, plus c. Now, let's do the other one correctly now. Whoops. Yeah, there's something wrong with my systems. I could sit here and wait, and like try to figure it out, but if it's not happening, it's not happening. I'm like 90% sure I made a very stupid error somewhere in there, and once I actually see it, if I am going to edit this, I'm probably not going to, because this is a very long video and I do not have the time for such things. I'm just gonna probably like slap myself in the head and be like, oh, dang it. But let's just do the next one, because we have been defeated for the first integral in some like 2 or 3 hours now. So we have the integral of 2x plus 1 over x plus 2 squared times x plus 1. This we also need to solve in the same way. I promise the antiderivative part would have been on point, okay? It was just the partial fraction decomposition. But the method that we use for that is still correct. We have a over x plus 2 squared. So for a repeated root, we do have to account for every root that's been repeated. So we have b over x plus 2, and then we have c over x plus 1, and that's going to be equal to 2x plus 1 over x plus 2 squared times x plus 1. So we're going to have a times x plus 2 times x minus 1, or x plus 1. Then we'll have b times x plus 2 times x plus 1. Or wait, a doesn't need to be multiplied by anything. It'll just be multiplied by x plus 1 to get x plus 2 squared times x plus 1. B will be multiplied by x plus 2 times x plus 1. Then c will just be multiplied by x plus 2 squared to get x plus 2 squared times x plus 1. And so let's plug in the zeroing factors. If x plus 1 equals 0, then these two terms will equal 0, and if x plus... Oh, why am I not being able to pause? Okay. 6 over 7, and, wait, what? That doesn't make any sense. Okay. Whatever. Okay. This is a very scuffed looking video. I'm incredibly tired. It's past midnight, but you know, I made a goal to myself that I'm going to reach some arbitrary long time. I was definitely aiming past 4 hours, but you know, 3.5 is nothing to scoff at. But yeah, so let's just do this real quick. We have 2 minus 8 over 7, which is 6 over 7. And then we minus 36 over 49, so 6 over 7 is going to be 42 over 49 minus 36, so 6 over 49. Yeah, that doesn't sound correct. Gonna have to use the dreaded calculator. Oh, wait, no. Wait. 6 over 7 minus 36 over 49, 42 over 49 minus 36 over 49, it's going to be 6 over 49, and then you divide that by negative 6, so you get b is equal to negative 1 over 49. Alright, great. So we have b is equal to negative 1 over 49, and that's correct, which is why I was kind of worried if I didn't calculate that correctly. But we have, let's plug that all back into our original. We will have a is equal to 1 over 49. So 1 over 49 times the integral of x, 1 over x with respect to x, plus, what was b again? That was negative 1 over 49, I think. Yeah, negative 1 over 49 of the integral times the integral of 1 over x minus 7 with respect to x, plus c, which we said was 8 over 7. 8 over 7 times 1 over x minus 2 squared with respect to x. And so this one is ln over x. I mean, not ln over x, ln absolute value of x minus 1 over 49. We can still use that ln trick. Ln absolute value of x minus 7. And then plus 8 over 7. U will equal x minus 2 squared. Du will equal dx. After you do du, dx is equal to 1. And then you just plug du back in. You'll have 1 over u squared, so u to the negative 2. And we've been doing this quite a few times now. The integral of u to the negative 2 is negative u to the negative 1. So we're going to have minus 8 over 7 times 1 over u, or u to the negative 1, and that is going to be 1 over x minus 2 plus c, or not x minus 2. I don't know where the 2 came from. It seems rather random. I guess maybe I was thinking of the actual squared, but we're going to have x minus 7 squared, and then we're going to have 1 over x minus 7. Alright, great. Let's see. What is the thing that we're going to do? Let's do this one. So this is going to take some stuff from algebra, long division specifically, and partial fraction decomposition to do calculus. So let's start with the nice and easy one. We'll have 7x minus 6 over x plus 1, or x minus 1 dx. Already, you might be thinking of ways to manipulate this to get this in terms of x minus 1, so you get like 7x minus 7 over x minus 1, and then, you know, plus 1, and you could do some weird stuff already, but we're trying to keep this by the books, so we're going to have to do this long division style. We have 7x minus 6, so biggest term, 7x divided by x is going to be just 7, So we have 7x minus 7. Subtract, we have minus 6 minus 7, so, well, minus 6 minus minus 7 is going to be minus 6 plus 7, which is positive 1. So we have 7 plus 1 over x minus 1. That's what this is. So we have the integral 7 plus 1 over x minus 1 with respect to x. We can use that ln trick. So we have 7x plus ln absolute value of x minus 1 plus c. So yeah, I mean, that idea is something that's going to carry over for the rest of this, but yeah, it's just kind of important. And then let's do some stuff. We have, interesting, we have x cubed and 1. So x cubed plus 0x squared plus, let me write the actual integral, it's going to be x cubed plus 1 over 1 minus x squared. I'm going to actually just factor out this negative and make this x squared minus 1. I actually already know how this will divide, but you know, just so that we don't spoil anything. 0x plus 1 divided by x squared minus 1. So highest power, x cubed divided by x squared, you'll get x. And that will be, well, let me write this correctly. You're going to have x squared plus 0x plus minus 1. Whenever you have any term that's not included in this trinomial, or like based on the power or degree of whatever terms you have, like for this x cubed plus 1, the highest degree is 3. So you have to have the degree plus 1 in number of terms. So you have x cubed plus 0x squared plus 0x plus 1, because you need to account for the 0x squares and the 0x for actually being able to do long division. So yeah, let's plug in x. We get x cubed plus 0x squared minus x. And then we subtract, you get x minus 1. And so you get x minus 1 over x squared plus 1. And, or not x squared plus 1, x squared minus 1. And remembering your factoring, you might know that x squared minus 1 factors to x plus 1 times x minus 1. So we can actually just cancel out the x minus 1s, and you'll be left with negative x plus 1 over x plus 1 dx. And so x to the 1, so you have negative 1 over, well, negative 1 over 1 plus 1, so negative 1 half, x to the 1 plus 1, x squared, plus ln absolute value of x plus 1. We can still do that ln trick, and I wrote that incorrectly. That is a negative. So that negative distributes. And yeah, that's another example. I think we're only going to do 2 more of these kinds of problems before we get into like improper integrals, and then maybe we might be able to get into some double integrals and some practice with multivariate. Just a little pinch of multivariate calculus, but you know, just a little bit. So we have the integral of x squared plus 3x plus 3 over x plus 1. So let's do that. We have x plus 1 divided by x squared plus 3x plus 3. We don't have to do any 0 stuff, so that's nice. Highest power, x squared divided by x is going to be x squared. So we have to remultiply x squared plus x. You subtract, you get negative 4x. And then you get minus 4. Or, wait, what? Oh. I just wrote that 3 incorrectly. I remember having done this problem, so it doesn't have a 4 as one of the factors. Let me just rewrite this. We have x plus 1, x squared plus 3x plus 3. highest power, you have x squared and x. So x squared divided by x is going to be x. Multiply that x back in, x squared plus x. 3x minus x is 2x, plus 3. So highest power, 2x divided by x is going to be 2. So 2x plus 2, when we multiply it back in, 3 minus 2 is going to be 1. So this will be plus 1 over x plus 1. And then we just do this integral. It'll be x plus 2 plus 1 over x plus 1. We just did this one, but for practice, 1 over 1 plus 1 is 1/2 times x to the 1 plus 1, so x squared plus 2x. Derivative of x is 1, so the antiderivative of 1 with respect to x is going to be 2x, and then, well, it's going to be x, and then you can redistribute the constant back in, and then plus ln absolute value of x plus 1, plus c. And, yep, that is yet another example of the same idea. And let's do one last partial fraction decomposition. Come on, get excited. Let's go. Woo! I feel like I'm going delirious. I need to drink some water too. Very thirsty. But, you know, math is more important. We have x squared plus 2x minus 3 and 7x squared plus 16x minus 19. Let me write the original equation. We have the integral of 7x squared plus 16x minus 19 all over x squared plus 2x minus 3. And you might be thinking, hey, why can't we just factor x plus 1, or x minus 1, excuse me, x minus 1 times x plus 3, and factor this and then cancel, but we can't actually cancel. But remembering that these two factors will definitely be helpful. Well, is it going to be helpful? I'm not sure if it will be helpful for this one. But, yeah, highest power, we have 7. X squared divided by x squared, we're going to have 7. So you multiply 7x squared plus 14x minus, oh, yeah. Yeah, this one's going to be annoying. But, I mean, you know, this is what we've been doing for a little while. So it's not going to be too bad, but it is kind of irritating. So we have 7x squared plus 14x minus 21. So we're going to have 2x plus 2. I don't want to make a mistake on this part because I actually do not have the answer key for this one. But let's just look back. We have x squared plus 2x minus 3. That is correct. 7x squared plus 16x minus 19. 7x squared plus 14x minus 21. Okay, subtract 2x. Yeah, that seems fine. And so we're going to have plus 2x plus 2 all over x squared plus 2x minus 3. And again, we're going to have to split those into factors. 7 plus 2x plus 2 over x minus 1 times x plus 3. So let's say that this is 7x, because again, you integrate a constant with respect to x, you will just get a constant times x. Plus 2, well, let's rewrite this 2x plus 2 as a and b. We're going to have the addition of two fractions, a over x minus 1, plus b over x plus 3 to get that LCM of a of x minus 1 times x plus 3. So we're going to have 2x plus 2 over x minus 1 times x plus 3. You multiply the x plus 3 to the a, so you get ax plus 3a. Multiply the x minus 1 to the b, so you get bx minus b. And then all of this equals 2x plus 2. So a plus b equals 2. And then 3a minus b equals 2 as well. So you add the 2, you get 4a equals 4, which means that a equals 1, which means that b also equals 1. Because 1 plus 1 equals 2. So we have 1 over x minus 1 integral plus 1 over x plus 3 dx, I keep forgetting that, but dx, and we just have that ln trick. Again, the ln trick only works if when you do u sub of that denominator and you find du, if du equals dx, then automatically you know that you're just going to have ln of u, and we know what u is. So that's the only reason why that trick works. It's not really a trick, it's just kind of doing u sub in your head and not like showing your work for it. But ln absolute value of x minus 1 plus ln value absolute value of x plus 3 plus c. Alright, so that's the last of these kinds of problems, but we do have some practice in improper integrals in a little bit, and we're just going to very, very briefly look at some multiple integrals, and we're not even going to try and visually see them, just like do them, and that'll be enough for today. Okay, let's go into some improper integrals. I did get a nice sip of water in. We're going to start with a combination of our favorite integration by parts. So we're doing the integral from 1 to infinity of ln x over x squared dx. Now let's set t, let's say t approaches infinity, so we're trying to find the limit as t approaches infinity of this integral from 1 to t. And then from here, we can actually do some integration by parts. Which of these is going to be easier to differentiate? Well, this ln x over x squared is just going to be one function over another function. So it can be also written as ln x times 1 over x squared, which is what we are going to write it as. So with ln x times 1 over x squared, how would we represent this? Which one of these is easier to integrate and which one is easier to differentiate? ln x, I'd argue, is a little bit easier to differentiate. So we have u is equal to ln x, du is equal to dx over x, and then dv is equal to 1 over x squared dx. So we have x to the negative 2. We did do this quite a few times, but it's 1 over negative 2 plus 1 times x to the negative 2 plus 1. So it'll just be negative x to the negative 1. So negative 1 over x. Let's say v is equal to negative 1 over x. And so when we do this, let's plug in what we have. We have negative ln x over x. We do need to replug in our bounds from 1 to t. And, you can just remember this limit as t approaches infinity is encompassing all of this, minus the integral from 1 to t of this negative 1 over x times dx over x, so negative 1 over x squared. And then, we just did the antiderivative of 1 over x squared, but that was just negative x to the negative 1. So this will come out. This will be a plus integral of 1 over 1 over x squared, but we know that this will again be negative. So this will be negative. We could just plug in t right now because we know that ln of 1 is going to be 0. So we can just disregard the second term. We have ln of t over t. That's all that needs to be remembered. Minus 1 over x with the bounds of 1 to t. And so that's just going to be negative ln t over t minus 1 over t plus 1 over 1, so 1. And then from here, we have to do the limit as t approaches infinity, right? So with the limit as t approaches infinity of all of this, we can say that as t approaches infinity, 1 over t, this one, will become 0. And then as t approaches infinity, 1 is not affected. Well, 1 by itself is not affected. So we can keep that in the inside the parentheses because we haven't done anything with it yet. But we have minus 0 plus 1. 0 is that 1 over t that we had. And then we can't, if we did ln of infinity, we would get infinity. And if we did t, which is going to be infinity, we'd get infinity. So we actually can't do that. We have to do L'Hopital's rule. Since both the numerator and the denominator are approaching infinity, we have to do the derivative of the numerator and the derivative of the denominator. So we're going to have 1 over t, or negative 1 over t, over 1 minus 0 plus 1. And let me rewrite this. We're having the limit as t approaches infinity. No, I'm leaving a lot of space, but minus 0 plus 1. And as t approaches infinity, 1 over t will approach 0. So you'll have negative 0 over 1, which is going to be 0. So you're going to have negative 0 over 1, which is 0, minus 0, which is 0, plus 1, which is going to be 1. Alright, so let's see another example. Okay, this is definitely interesting. Alright, let's see. I think we could do this. It's definitely rather odd, but it's possible. So that's the most important thing. We have the integral of 1 over 1 plus x squared from negative infinity to infinity. And now if I haven't mentioned this definite integral property beforehand, I really am not good at my job, because if you have, you can split these bounds based on any value that they share in common. So you can go from, say, negative infinity to 2, and then go from 2 to infinity. And that's equal to if the actual integral itself is the same, f of x dx and f of x dx, this sum, regardless of what value this is, will be the negative infinity to infinity definite integral of f of x dx. It doesn't have to be negative infinity to infinity. It can be any value, any real value, but, yeah, that's just a property of integrals. I do probably need to mention that. So for this one, we'll have to split this into 2 improper integrals. We'll have the integral from negative infinity to 0 of 1 over 1 plus x squared, and then plus the integral from 0 to infinity of 1 plus 1 over 1 plus x squared dx. Okay, so what is let's say, we can do a and t, I think. You know what? Since we have 2 of these improper integrals that we're trying to solve at the same time, I'm going to actually use a and b, but, t obviously also works. But we have the limit as a, so used to saying a, t, but the limit as a approaches infinity of the integral from negative, well, which one are we going to do first? We'll say that a approaches negative infinity. Limit as a approaches negative infinity of the integral from from positive a to 0 of 1 over 1 plus x squared dx. And this one, I think we know at this point, is just arctan. So we have the limit as a approaches infinity of, or negative infinity of arctan x, and then we have the bounds of 0 and, well, 1. Wait. Oh, not 1. I was thinking of something else. It's a 0 and a. So we're going to have arctan 0, which is 0, and arctan a, which is a. We're going to have the limit as a approaches negative infinity of, arctan 0 is 0 minus arctan a will be negative arctan a. So, yeah, I'm not actually sure what this limit is. I've seen it before. Hold on, let me search this up real quick. Arctan of okay. Huh. Interesting. Okay. So this limit's supposed to be just pi over 2, which I mean, it's fascinating. I need to do more research about it, but I have honestly never seen that before. So, we learn something new every single day. But yep, the limit is apparently pi over 2. And let's do the limit as b approaches positive infinity of this same limit from 0 to b. Now from here, arctan is still arctan, so we're going to have the only thing change be our bounds from 0 to b. So you plug in arctan b minus arctan 0, and you'll just get arctan b, because arctan 0 is again 0. So let's see what arctan of infinity is. I have a sneaking suspicion it might be just pi over 2, but who knows? And yeah, it apparently is just pi over 2. We have the limit as b approaches infinity. Maybe it was actually because arctan is not a even function, so if you do negative arctan of a negative number, you'll get arctan of a positive number. And then, yeah, so arctan of negative infinity will probably be negative pi over 2 or something, but since we're doing negative arctan of negative infinity, we just get arctan of positive infinity, which is pi over 2, which means that arctan b is also pi over 2, which means that when we add these areas under the curve together, you get pi over 2 plus pi over 2, which is pi, just pi, which is really cool. So yeah, I mean, that's just kind of dope. Let's just go into some other interesting stuff. Okay. Ooh, it's like a piecewise function. Okay. Yeah, no, I don't think we should do that. Yeah, I think we can do another example. We have the limit. Oh, not the limit just yet. We have the improper integral from 0 to 1 of 1 over. Actually, no, I think I actually did this one already in my advanced limit video. Not advanced limit video, advanced integral video. I think I'm gonna have to skip that one. Let's see what other examples we have. Okay. Ooh, interesting. Okay, so let's try this one. We have 1 over 3x plus 1 squared. So we have the integral from 1 to infinity of 1 over 3x plus 1 squared, right? And then dx. And then this is also the limit as t approaches infinity of the I can speak definite integral from 1 to t. So let's do this. We have u equals 3x plus 1. We say a function within a function, so we u sub. Du will equal 3dx because du dx will equal 3, and then we just, distribute the dx. Derivative of the constant is 0, so that does not affect it. That means that dx is equal to 1 over 3 du. So we can plug that in. We'll have, we can bring that 1/3 out as well. We'll have 1/3, we can still keep that 1 to t, and then we'll have 1 over u squared times du, and we said that what did we say? We said that, oh, this is negative u to the negative 1. So we're going to have 1/3 times negative 1 over 3x plus 1. U is equal to 3x plus 1, so negative u to the negative 1 will be negative 1 over 3x plus 1, and then we plug in t and 1. So we're going to have 1/3 times, we're going to have 1/3, not there, 1/3 times negative 1/3 t, 1/3 t plus 1. Okay, interesting. Minus 1 over 3 plus 1, so 1 over 4. And we do the limit as t approaches infinity of all of this. I'm just going to, multiply that 1/3 across. So we're going to have, negative 1 over 9t plus 3. And then this will be minus, so plus 1 over 3 times 1 over 4, so 1 over 12. And then as t approaches infinity, 1 divided by an incredibly large number will be an incredibly small number, so this limit will approach 0, and 1 over 12 is a constant that is not affected by any change in t, so this limit will just evaluate to 1 over 12. Okay, that one was fun. Relatively. What else do we have? We have some, that's a interesting looking one. Okay. Not sure if I can do it though. We'll see. Okay, so this one is definitely interesting. This will make, I'm not sure if this is too much of improper thinking, but it is a lot of manipulation. So, we want to be excellent manipulators, not in real life, but in math. So we have the integral from 0 to infinity of e to the x and e to the 2x plus 3. When you have e to the 2x, it's probably best to think of e to the 2x as e to the x squared before you try and do anything. And now, you might be thinking there's something that we can do with the formula that we've been using quite a bit recently. That is 1 plus 1 over x squared. We have e to the x and we have e to the x here. So if we could, manipulate some stuff, maybe get this 3 to be a 1 somehow, and then get this x squared to be, e to the x, there could be something there. But that is a lot of steps. So let's first try to get this 3 in terms of 1, divide everything by 3. Seems simple enough, right? And then once we have that, we have e x squared over 3 is equal to something, and, well, plus 1. Oops, I can write this correctly. Plus 1 over e to the x. Might be some way to factor out e to the x's so that we get 1 over something squared, but before that we do need to rewrite that e to the x squared over 3 in terms of something a little bit more palatable. That's not going to be, easy to work with, so we have u squared. This will be, we'll write this as u will be the square root of e x squared over 3. So we're going to have square root of something squared is just going to be that something. We're going to have e to the power of x times the square root of 1 over 3, which is just going to be root 3 over 3. Once you, rationalize the denominator, in case you have forgotten, I won't blame you, I forgot a little while ago. It's just root 1, root 3, 1 over root 3 is not the nicest way to treat your fraction, so you multiply both the numerator and the denominator by the radical, and then the radicals cancel out, so you get 3, and then root 3. So, yeah, you're just going to have root 3 e to the x over 3, and now there's something there. You know, we have a 1 plus u squared format, and now we just need to make that e to the x follow the same kind of rules, right? So let's do du. Well, actually, let's see. I don't know. I don't think it's really necessary. Well, once you divide every term by e to the power of x times root 3 over 3, you should just get this. Like, let me think. So if you do du of this, right, root 3 over 3 is still going to be a constant, so it doesn't actually get affected by anything. You're going to have du is equal to root 3 over 3 e to the power of x dx. And so dx will equal 1 over all of this du. So let's put that back there. And when you do dx times 1 over all of this, it'll cancel out with this. So you're going to have 1 over root 3 over 3? No, it'll be 1 over 3 root 3. So let's just take out this root 3 over 3. It's starting to get a little bit crowded. Let's try and take out this e to the power of x, and because we want this e to the power of the x to cancel out with this e to the power of x once you have that dx. Du, wait, du is equal to that dx. So there's definitely something that I'm missing here, but I'll just kind of skip to the answer. It's getting a little bit late for me, but So I think there is something about how when you do du dx to get dx, and then you plug it back into the formula to get du, you should get root 3 over 3 in the numerator times 1, times du. Not root 3 over 2, root 3 over 3. And then from there, du over 1 plus u squared, that's just going to be arctan u. And then this is multiplied by root 3 over 3. And then when we replug in our arctan being, or u being root 3 over 3 times e to the power of x, and you do this limit as, well, you plug in x equals 0, or not x, you plug in t as t approaches infinity. You just, we said that, what am I saying? When you do all of this, and you just plug in t equals infinity for arctan like has a defined limit as, it approaches infinity, and that will have your final answer be root 3 over 9 times pi. That's somewhat weird. I kind of sort of get it. Like, I know how you get to arctan. Like, I mean, I figured that much out. But something with my u sub is messing up what I'm actually getting, and it's a little bit annoying. But, we can just keep on keeping on. And let's go to another example. Let's see. the integral, I don't think I've done this one, the integral from 0 to 1 of ln x over root x dx. Now we're going to have u is equal to ln x, and du is equal to 1 over x, because ln x is definitely going to be easier to integrate, easier to differentiate than x to the power 1/2 is to integrate. So we have dv is equal to x to the negative 1/2 dx, and if we just add negative 1/2 plus 1, you get 1/2, so 2, well, 1 over 1/2 is 2. So you get v is equal to 2 x to the 1/2, and then from there, you just do uv, so ln x times, something's up. I forget which one's actually it can't approach, because it's probably 0. Actually, no, it's definitely 0, because if you plug in ln 0, you do get something. Wait, do you? No, because ln can't equal 0. It can't. No, ln 1 can equal 0. I know that much. But I don't think you can plug in ln 0. I know for sure that you can't plug in square root of 0 to get ln over something over 0. So, we'll just be approaching t, maybe approaching 0 from the right. Yeah, because square root can never be negative. Okay, so we'll be doing the limit as t approaches 0 from the right of the definite integral from t to 1. Let's see if this is correct. So we'll have ln x, so uv, 2x 1/2 ln x of 1 to t, or from t to 1, minus the integral of v du. So it'll be, we can bring that 2 out, and we'll have x 1/2 times 1 over x, or x to the negative 1/2 dx, and we just calculated that one. We said that this is going to be negative 4 over, or 4x to the 1/2. Let's see if that's correct. Minus 2, x to the negative 1/2. Yeah, it seems fine. Yeah, no, I think that's correct. And then we still have the bounds of t to 1. So let's plug that in there. And, not 1 to t to 1. So you'll have 2 ln, or 2 times 1 times ln 1, which is going to be 0. And 2 square root t times ln t minus 4 minus, well, this is going to be negative 2 root t. Negative 2 root t ln t. Right, minus 4, just 4 times, oh man, this is going to be an indeterminate form. Yeah, no. Let's see. Minus 4 root t, so plus 4 root t. There might be a way to do some stuff. Plus 4 root t. Then we could factor out the root t's and get something. But will that work? This is going to be ugly. Let's see. Maybe I should have rationalized the denominator at the very beginning. Let me think about this for a second. Oh, wait, no, never mind. We're good. I was thinking about t approaching infinity, and I thought that we would have, like, infinity times infinity, which is an indeterminate form, and we'd have to do a bunch of L'Hopital's and, like, manipulation, but we don't have to do any of that, which is really nice. We only have to do the limit as t approaches 0 from the right, so ln can obviously never be negative. it's the inverse of an exponential function, and exponential functions can never have negative values. So t will always be greater than 0. So when you approach 0 from the right, you'll just get a very, very small value. And if you just direct substitute 0 for these, you'll get negative 2 times root 0, which is 0, and 4 times root 0, which is also 0. So ln of 0 is the only thing that doesn't actually exist. And, well, I mean, the limit as t approaches 0 does exist. It'll be 0. But you can just kind of think of it as if you have, say, a really, really small number, like 0.000001, and then you have e to an even smaller number to get to that 0.0001, you will have a much, you have a very, very small number. That's all it's saying. And then 0 minus 4, so you're just going to have negative 4 if this limit is t approaching 0 from the right. I was scared because I thought it was t approaching infinity, and I'm like, oh no, I've done something very wrong. But luckily we have not, so we can just continue. I think I'm going to do maybe 1 or 2 more. Let's see. We have square root of 1 over we have the integral from 2 to 3 of 1 over 3 root 1 over square root of 3 minus x. So let's say, since, x can't equal 3, we have 1 over 3 minus 3 in the denominator, so it's going to be 1 over 0. We're going to have the limit as t approaches 3. I think it'll be approaching from the right, or no, from the left, because you can't have a negative value. So it'll be t approaching 3 from the left, and we will use t instead of 3. So the integral from 2 to t. I don't know why I'm having so much trouble with that word, but here we are. We have u equals 3 minus x, du equals negative dx, because du dx is equal to negative 1, which means that dx is equal to negative du. So we have negative 1 over, well, let's just write this as it's supposed to be, negative 1 times u to the negative 1/2, right? And then this will be du. So we do 1/2 plus 1 to get 1/2. 1/2 times u to the 1/2, or, well, actually, this isn't correct. It'll be 2 times u to the 1/2. 2 times u to the 1/2. And then we will be doing this negative. Let's see if that's right. So let's plug in our u back in. We'll have negative 2 times 3 square root of 3 minus x. Let's see. 3 minus x 1/2. 2 times 1/2. Okay. I think that's correct. We'll see. And then we will have the bounds from 2 to t. So when we plug in 2 and t, we'll get negative 2 root 3 minus t minus or plus root 3 minus 2, which is going to be 1. So we have plus root 3 minus 2, which is just going to, we're going to have minus 2, well, we're going to have minus 2 times the square root of 3 minus 2, which is 1, so we're going to have minus 2, which is just plus 2. So plus 2, and then we substitute 3 in, we have the limit as t approaches 3 from the left, so when we direct substitute 3 back in, we're going to get 0, and so our limit will just be approaching 2, which is correct. Okay. Ooh, this one's ugly. I mean, it's not ugly, but it's definitely annoying, or at least it looks annoying. We'll try it though, because what do we have to lose? Yeah, no, this is very not great, but we can do it. we can do anything. So we have the limit. I'm not sure if we can do this. This one's going to be hard. We have the limit from 1 to infinity of e to the negative square root of x over square root of x. Of course, we cannot have infinity, so we will be approaching infinity. We have limit as t approaches infinity of this monstrosity. And how do we even integrate this? Good question. I need to come up with an answer. Would we do u sub? Would we do u sub? We might do u sub. Yeah, so wait. Oh no. No, this isn't, I wouldn't say it's like easy or anything, but this is totally fine. Like, we can do this. So we have u can equal negative root x, and then du, if this is negative x to the negative, or x to the positive 1/2, we just bring that 1/2 out. Then we have negative 1/2 times x to the negative 1/2 dx. So yeah, this is, pretty standard. And then when we divide to get to dx, we have negative 1 over negative 1/2, so negative 2, and we have 1 over x to the negative half, so it's going to be x to the positive 1/2. And already you can kind of see where we're going to go with this. We have this is du, and this is equal to dx. So with dx right here, we can cancel out the x 1/2 and the x to the 1/2. So we just left with negative 1 over 2? Negative 2, I think. Yeah, just negative 2. So we'll bring that negative 2 out there. It's a constant from 1 to t. And then we'll have just e to the u du, which is honestly rather beautiful at this point. We have e to the u, plugging in t and 1. So we'll have negative 2 e to the t minus e to the 1. So what's that going to be? It's just going to be, wait, what? Huh, let me think. We should get 2 over e, which, I mean, we do have 2's and we do have e's, but we do not have 2 over e, at least yet. Let's see what we're doing. I think that's correct. Like, I know that's correct. Maybe it's something with the, like, when you change the u sub, you have to change the bounds or something. Oh yeah, obviously. What is wrong with me? No, this isn't e to the u. This is e to the negative root x. So we have e to the negative root x. We can bring that negative 2 back in just because, and we'll just plug in t and 1. So yeah, no, I was losing it. We have negative 2 over e to the square root of t. Yep, negative 2 over e to the square root of t. And then you have minus, so plus 2 over e to the square root of 1, so e to the 1. And then once you plug in t, or once you think of t approaching infinity, you'll have e to the square root of t approaching infinity, and 1 over infinity, or 2 over infinity, or any number over infinity is going to be approaching 0, because if you divide a normal number by a very, very large number, you will get a very, very small number. So this will approach 0. 2 over e is a constant. It will not be affected by any change in t, so we will have 2 over e. That's our limit. I think that's about it for now. Yeah, I mean, the other examples, they're not the greatest. Yeah, like, they have a bunch of diverging improper integrals, which I don't think we have the time to really delve into as much as we should, though. We might be able to talk about them in a series and very briefly go into convergence and divergence, then maybe we'll be able to get into improper integrals and talk about that a little bit. But just to round things off, let's do some very, very basic multiple integral practice problems. Let me try and find some. Integral practice. Okay. Hmm. Eh, yeah, we'll see. I don't. I'm not actually sure if we can do anything right now. Um, this is all the practice problems that I'm seeing currently. We could do some of those fx, is equals constant values and then, do those. But we already did a practice problem with that a little while ago, and it's already about 1:40 a.m. And I very much do not have the time to teach multivariate calculus. So I think, unfortunately, I'm going to have to stop it now. I do need to sleep because I don't think I cannot sleep. But, this was, I was about to say fun, but I think an experience is probably a better descriptor. This was an experience. I'm tired and my feet hurt for some reason, but it's whatever. I'm not even standing. I'm very much sitting, but you know, uh, so yeah, this was a long video with quite a bit wrong in it. So if you did not like this video, totally understand. But I do have, man, I really wanted to have an album recommendation. This would be a very good opportunity to recommend the Epic, but I already did that one. This was a very long video though. The Epic is beautiful, and you should listen to it. Man, usually I try to recommend albums that I have been listening to like consistently recently, but I swear I'm not in my feelings. It's not that I have like fallen in love or anything. It's not like I'm going through a bad breakup, but I have just been listening to Leanne LaHavas's self-titled record, one of the first like albums that I've ever recommended on this channel. I've been listening to that almost on loop. I swear. Bittersweet, that first opening track, I think I've listened to it at least 100 to 200 times over the past week. Honestly. Honestly. I'm not doing anything. It's not like I'm working or I'm just listening to this for the sake of listening. I'm not even getting sad anymore. I'm not feeling obviously feeling everything because she's one of the greatest singers that I've heard in our recent generation. But I mean like it's almost blasé at this point because I've just been listening to it over and over again. But yeah, I mean, I've already recommended it, so it's not gonna work. Uh, let's see. I did listen to an album that I thought was pretty good. Uh, could recommend that Kaytranada AP, like LP, 99.9%. But honestly, I'm more of a fan of Bubba, so I mean, if I'm gonna recommend anything, it's gonna be the one that I personally prefer. Uh, have been listening to a lot of Blackbird. Um, I've been listening to some Metallica, which is not a sentence that I wanted to say. I've been listening to some Iron Maiden as well because of a friend's recommendation, but honestly, I don't know. You know? Huh. Well, let's see. I have apparently listened, well, listened to, come on, I know I have music, okay? I listen to music. I listened to quite a bit of Doja Cat recently, but I mean, you know, well, I can recommend Doja Cat, and you should probably listen to Her Planet, Her album. It was very good, but I mean, I feel like that's probably not the best place to go for this. I listened to some Dusty Springfield the other day. Didn't listen to a full album or anything, but I listened to some of her like quote unquote best tracks. Uh, let's see. I'll look through my Spotify. We have a lot of Rina Sawayama. I mean, like, just listen to Sawayama, please. Listen to Sawayama. It's just one of the best sophomore efforts I've seen, honestly. And it's not even her sophomore effort. I think she's like released a couple EPs, but it's just brilliant. Everything on that album is just it's brilliant. Uh, it just has this like energy and this like ferocity. But yeah, I can't recommend that. Marvin Gaye, is that appropriate? Like not obviously not appropriate for this audience because everybody likes Marvin Gaye, but more like is that appropriate to recommend because who hasn't listened to some good Marvin Gaye? I don't know. I feel this like odd pressure to like get into something. I think I might have actually not recommended Diodato. Oh no, I have. I have. Let's see. Ahmad Jamal Trio. Did I? Let me see. Did I ever recommend that album? I did not. The Awakening. I used to listen to this all the time. It was like my study album of choice, but The Awakening by Ahmad Jamal Trio is very beautiful. I mean, it's not like, well, it is kind of groundbreaking, but it's definitely not like unheard of in terms of jazz. It does definitely fall into the same like niche that most jazz falls into, but it's just good. It's well performed. It has a lot of energy. It's doesn't overstay its welcome, even though some of the songs do reach like 6, 7 minutes. They usually kind of go past pretty quickly. Piano is always on point. It's well done. It's well performed. It's very tightly composed. I mean, you know, it's just a very well constructed jazz album, and I used to listen to it all the time. So yeah, I did manage to find a single recommendation that actually works. So I'm gonna count that as a win. If you like this video, which I mean, if you did, I mean, wow, I did not like this video. I didn't like filming it, didn't like saying it, didn't like doing it. My voice hurts. But if you like this video, please comment down below. If you did not like this video, constructive criticism is always encouraged. And this video does need quite a bit of constructive criticism. And if you're not in the mood for constructive criticism or a comment, then you can run a kilometer. I think I did run a mile a little while ago, but you can run a kilometer. All right. Bye.